as well as public policy. So after my stint with government, I had the opportunity to join LSO. And really that opportunity was seeing within government how the sector is viewed. And as I said, I knew that we had this huge opportunity, this potential, and we weren't really fulfilling it. And I felt like there wasn't a strong voice out there talking to government and informing government about our story, about our narrative. And so that's why I joined LSO. Now, when I talk about life sciences, I'm not just talking about the health sector. So not just pharma and medtech. I know that's where our minds typically go. But life sciences is much more than that. As I said, it's that diverse union of stakeholders. So it's everything from industrial biotech, agri-food biotechnology, and even biofuels. Think about life sciences where the science part is the platform on which the sector's built. It's very similar actually to the IT sector, right? It's really a knowledge economy on which companies and technologies are built. In terms of our organization, we've been around for a long time, since 1989. No, I have not been with the organization that long. We are fully member funded, so we don't receive any support from the government at any level whatsoever. It's all through our members that are supporting us. And it is a diverse group of members, which I'll talk about in a moment. But we really focus on three main activities. So I talked about advocacy. So we want to be a strong voice for the sector. So we're registered lobbyists both federally and provincially. We have a different sort of approach to lobbying though, because we represent an ecosystem. So that gives us a lot of credibility when we're speaking to government. The second thing that we do really well is we serve as a central hub of connectivity for our sector. So if you want to know what's going on within life sciences, you want to connect in with LSO, you want to be part of our publications, you want to attend our events. We love making connections. If you're having a problem, either as a company, as a business, or a young professional seeking your next career path, connect with us, right? If we don't have the answers, we probably know somebody that does. And then the third thing that we do and we focus on is we believe that it's not enough just to ask government, what can you do for us? We need to be proactive in growing our sector. So we focus on programs that help grow our sector. So we have support programs for SMEs, discount purchasing programs, et cetera. We have a scholarship program, we have mentorship programs, we have a job board. And so those are sort of ways that we contribute to the growth of our sector. This is a little flavor of our members, and I'm showing this up there not to overwhelm everybody or make you squint to read all of these logos, but what I want to get across here is that technically we're an industry association, but I like to think of us more as a community organization, because it's everything from academic institutes like Carleton University, right through to service providers. We have student members, we have companies big and small. So it's that whole ecosystem that we represent that really kind of differentiates our organization. All right, now I'm going to talk about the opportunity, that massive opportunity that I alluded to at the beginning. So you don't have to actually look very far to quantify what we're missing out on. So if we just look south of the border into the US at the NASDAQ, the three largest biotech companies listed on the NASDAQ are Amgen, Gilead, and Moderna. They have a combined market cap of 323 billion US. Now let's put that in a Canadian perspective. Our entire oil and gas sector, right, which is a huge portion of our economy, that's 128 companies listed, publicly listed on the TSX and TSXV. Those three biotechs surpass the combined market capitalization of the entire Canadian oil and gas sector. That's massive. But what's really interesting about those three companies is those aren't companies that are, centuries old. Those are companies that are decades old. In fact, most of us probably even never heard of Moderna before COVID-19. So they're based on good science, and then they achieved rapid growth to have huge economic and social impacts. So this is what we need here in Canada. We haven't seen these types of success stories yet here in Canada, and we need to be asking ourselves why. What's missing? So we've also quantified this opportunity in more regional ways as well. This is from a study we did with Deloitte back in 2019. And what we asked Deloitte to do is take a look at our sector and see how are we performing over time, and then project out forward. And we are a growing sector. And Deloitte said we would continue to grow at a fairly decent rate if we did nothing at all. But if we looked at other jurisdictions that were more intentional, more strategic with their public policies around life sciences, we've seen accelerated growth. And so they extrapolated that data into an Ontario context. And what they showed was that we could really accelerate our sector, and we could have huge impacts, and there could be a huge return on investment in developing a more strategic approach. And in fact, we could add over the next decade nearly $30 billion to our GDP based on life sciences contributions, and nearly 100,000 new jobs just in Ontario. We're not the only ones doing this, though. The rest of the world is looking at this, especially now post-COVID, right? Life sciences is on the radar of everyone. I had the opportunity to see this gentleman, Professor Ostwald, at a Walrus event a few months back. And he's done a lot of work in the EU at measuring inputs and outputs of investments into health GDP expenditures and what it means to GDP productivity in the EU. And time again, what he's shown in every jurisdiction that he's looked at is that for every dollar that governments invest, they get more than $1 out in terms of GDP productivity. And this is really important, particularly in regions with publicly funded health systems where, like Canada, we often view these expenditures as a cost. They're not a cost. These are investments, right, that we're making in our society in terms of our productivity, et cetera. And there is a tangible and measurable return on these investments. So that was a little bit about the opportunities that we have. So where are we now as a sector? Well, here in Ontario, we do quite well. Again, this is from that Deloitte report in 2019. We have significant contributions to our provincial GDP. We employ about 90,000 people in the private sector directly. When you include indirect and induced jobs, it's closer to 200,000. And we're significant contributors to the government coffers as well. Now, a little question for everyone here. I told you the significance of our sector. If we include, so that was just the private sector. If we included the public healthcare system and public employees that were captured within life sciences, do you think we would be the largest industrial sector? Let's see a show of hands. Who thinks we'd be the largest industrial sector in Ontario? All right. Who thinks we'd be the second largest? Third? All right. Well, I think most people were right. We would actually be, in fact, the largest industrial sector. Right now, ICT and financial services are really the two largest. But if we included public health, we would actually catapult above both of those. And in fact, if you include public health care, about 1 in 13 Ontarians are actually employed in some job that is connected into the life sciences sector. So again, really significant impact on our economy. Now, I mentioned too that we have a lot of these strengths and ingredients that make us really competitive in terms of jurisdiction. We do have, world-class academic institutes. I think that is number one on my list. Our science is world-class, bar none. We've got great accelerators and incubators. We have diverse population. We have a lot of these elements, but we're still missing some areas here. There's still some gaps because we haven't achieved that success. So what are those gaps? Well, I'm going to point to some of them. It's not going to be a comprehensive list, but there's a few that I think we can point to. I really like this chart. It's a bit dated. Again, it's from 2019. This Global Innovation Index, they do this annually, and newer data is available, but they don't present it in the same way. So I'm going to use this data, but not much has changed. So this is a chart on the metrics for the quality of innovation in terms of the top 10 high and middle income economies, and Canada's ranked here at number 10. But take a closer look at the elements they're using to measure these, the parameters. So the first one, that first blue bar there, that's the quality of our universities. And you can see if you just look at that piece, Canada would actually be probably in the top 5. Now, if you look at the far end, that pink bar, that's citable documents, so that's peer-reviewed publications. Again, it's a measure of scientific output and quality of our research. And again, if we just looked at that element, you can see Canada would rank closer to the top. So where do we fall down? Well, it's that middle bar, that little purple bar that you see there in the middle. And that's patent families filed in 2 or more offices. That's a measure of our ability to take that scientific research and then translate that into intellectual property. And that's where we seem to be tripping up. Now, why is that? Well, there could be several reasons for that. I'm going to point to one, and it's a bit controversial, so there are probably going to be some people in this room that might say that, might argue this point with me. But I think one of the reasons that we fall down here is that we don't have any standardized framework for how IP is developed and shared from publicly funded sources. And jurisdictions that have managed to do this have succeeded in translating that research into technology more nimbly than we have. So the US is a prime example. They have something called the Bayh-Dole Act in the US. So when you have research that is supported through public dollars and you have a private company coming into, let's say, to an academic institute and they want to license that product, there's a set amount of the benefits that go towards the PI, the institute, back to the funding agency, and it's well defined. Israel's the same way. In fact, a few years back, I was able to join the Ontario government on a trade mission to Israel, and we visited all sorts of research institutes. And without exception, every single one started their presentation with a slide that says, this is how we share the benefits of IP. And it just broke it down. It was fundamental to how they commercialize technology. So I think that's a gap that we have here in Canada. All right, another really old and dated slide, but it illustrates a point, and I would suspect that it's still quite relevant. So I'm really interested as a scientist and somebody that's worked in public policy when there's a disconnect between public policies. And I feel for a very long time in this country, there has been a disconnect between our education policy and our economic policy. What do I mean by that? Well, I think we all know that we really value STEM education. And our policymakers, our government leaders have valued STEM education to the point where they're willing to invest taxpayer dollars into supporting STEM education, into promoting STEM education. And that's a good thing for our sector. We want that. But look at the Canadian economy. We are rooted in natural resources and traditional manufacturing industries. That's the backbone of our economy. And all of our industrial strategies for decades and decades have really focused on that. And when you talk to policymakers within economic development agencies for a very long time, they said, yeah, you know, knowledge economies like life sciences are great, but they're the economies of the future. They're not the economies of now. And that is a mistake. And so that's where we see this policy disconnect, where we see we're training very well workforce within knowledge economies, but our economic policies are disconnected. Now it's starting to change a little bit, particularly post-COVID. I'll talk about that in a minute. The other reason I think we have been unable to succeed in developing these success stories is that life sciences is really hard for policymakers to get their head around. Why? Because there's no Ministry of Life Sciences. We have a Ministry of Health, we have a Ministry of Colleges and Universities, we have a Ministry of Economic Development, sometimes we even have a Ministry of Research and Innovation. It's everywhere. We have a Ministry of Agriculture. Life Sciences touches all of these. So how does government then structure itself to break down the silos of these ministries to understand and align policies to support this really diverse, multifaceted sector? That's a tough one. And in fact, that's one of the things that we've been saying for many years, is that if government is serious about being strategic and intentional about how they support life sciences, they need to take an all-of-government approach. All right, So back to the pillars that we have, and just so you know, this slide is actually taken from a report that we issued. It's available on our website about a roadmap to a more integrated ecosystem. So imagine we take all of these strengths and now we fill these gaps, with a competitive and receptive innovation environment, with better access to capital, with that framework for IP, all of these things working together. Then I think we can start working towards fulfilling that full potential of our life sciences industry. And Kevin Lynch actually summarized this really well. He said, this was at an event that we host annually, and he was a keynote. And he said, we have all the ingredients, but we lack the recipe. Well, that's not exactly true. We've actually had lots of recipes over time, dating back to the 80s. And these are few of the ones that have stood out to me, and some of them were fantastic. I would point to the one in the middle here, An Action Plan for Prosperity by John Manley and Paul Lucas. Fantastic document. If you can look that up, it's I think 2 or 3 pages, very concise. And they just lay out very clearly what needs to be done. And it's still very relevant today. But we've seen tons of these strategies come and go, and we haven't really seen the results at the end of them. And now we have 2 new strategies. We have the federal biomanufacturing and life sciences strategy. What makes this different this time around? Well, number one, I feel like the government listened to what we were saying. The first pillar is a strong and coordinated governance, particularly an all-of-government approach. The other thing that I really like about the strategies that are being implemented right now is that they're not looking at these as one-and-done strategies, but rather they're engaging the sector in a meaningful way about, okay, we've done some initial investments, most related to the pandemic and pandemic preparedness, pandemic response. But now we recognize that this is an industry that we need to have continuous development. And so how do we work with the sector to do that? So a very different approach than we've seen in past. And same at the provincial level. We now have a provincial strategy that was announced last year, and again, some initial investments that were made and initial announcements. And that was phase 1. They've actually broken this one into 2 phases. In phase 2, they've created a life sciences council. I'm very privileged to be the chair of that council, and one of my council members, Maura Campbell's here this morning as well. And we're advising the government on several areas that they should be looking at. And that advice is then going to be taken into what will become phase 2 of the evolution of the Ontario Life Sciences Strategy. So again, it's a co-creation that's happening, and we've never seen that before. So I'm really excited and optimistic about these federal and provincial strategies. But what it comes down to is we've had lots of recipes, we've got all the ingredients, now it's time to get cooking. But implementation is not easy. And again, this is a slide I really love. It's one of my favorites. And I shamelessly stole it from David Naylor. He presented it at one of my events, and I swiped it. And I think it just speaks volumes about how hard it is to actually succeed in these sorts of initiatives. Because you really have to have everything aligned. The stars have to be aligned perfectly in order to have meaningful change. And if you're lacking in any one of these areas, you won't succeed to the full potential. There are still some challenges that we face, and one of the big ones is a perception challenge. Again, this is a very Canadian context. I talked earlier about, when we have publicly funded health systems, about this concept of cost versus value and return on investment. And that's something I think we struggle with in Canada. I'm pretty certain if you ask 10 Canadians, 9 of them would tell you that we have the best health system in the world and it's absolutely free. And neither of those 2 things are true. Not even close. And then you introduce a private sector like Big Pharma. Ooh, yeah. And then all of the baggage that comes with that. And that's a tough one for Canadian life sciences. And even in the wake of the pandemic, Big Pharma just saved the world. I don't think that that's an exaggeration to say. They just saved the world. But they're still fighting these perceptions. And a lot of it is, I think quite unfounded as somebody that's worked in this sector for decades. So let me give you an example here. J&J, they're the biggest pharmaceutical company globally. Now, if you look at the Fortune Global 500, they have companies listed, top 500 global companies listed in terms of revenues. Where do you think the largest pharma company in the world ranks? Who thinks they're top 10? Show of hands. Anybody think they're top 10? Okay. Anybody think they're in the top 50 but not top 10? Okay, a few more hands. How many think they're in the top 100 but not top 50? All right, a lot more hands there. Who thinks they didn't make the top 100? Okay, a few hands. So it seems most people think that they're in the top 100 but not top 50. They're actually at about, I think, 103 this year. They've hovered around 100. I've followed this for about a decade or so. They sometimes have dipped down into like the high 90s, but mostly they're outside the top 100. The top companies are Walmart, Apple, Toyota, I think, is up there, some oil and gas companies. It's really interesting to think about the perceptions around those companies versus the pharma industry, and thinking about the societal benefits that life sciences companies like J&J bring to the table and the impacts that they have. This is played out, if we go pre-pandemic, this perception, I think, around the pharmaceutical industry played out as a very adversarial relationship with the federal government here in Canada, in something called the PMPRB, the Patent and Medicine Pricing Review Board. And in fact, this led to all sorts of lawsuits, and actually the majority of which the industry won, because the agency, PMPRB, was actually exceeding its mandate legally. So they lost a lot of these. But can you imagine now that you've got this relationship, this very adversarial relationship that's happening, and then you're hit with a pandemic, right? And think back to that time, right? We didn't have a strong relationship. Our government and the pharma industry did not have a strong relationship. In fact, the total opposite. And that's why I think we saw our federal government looking elsewhere for solutions initially. And eventually they had to come together. They were forced together. And actually, I think that was a good thing, because it created the basis for a new relationship going forward that we're seeing today. But the impacts of this adversarial relationship, I think a lot of Canadians don't realize what had happened in the background, because there are complex regulations that were happening. But what we saw, and we worked with IQVIA to do this research, was we actually saw companies, global companies, delaying launching medicines in Canada because of the uncertain regulatory environment and the uncertain reimbursement environment. And in fact, most of the products, over half the products that were launched in the 2 years leading up to 2019, hadn't made it to Canada. Over half, and most of those were oncology and rare disease products. So Canadians were missing out on these very new, innovative products. And this isn't, reformulations or Me Too products. These are new, innovative medicines, high-impact medicines. In a follow-up to that study we did with IQVIA again, we showed that over the last 20 years, Canada as a launch country for new medicines usually ranked about 4th. And during this whole PMPRB fiasco, we dropped down to about 9th. But COVID-19 was that wake-up call. And I think it reset that relationship. And we've started to now move on from things like PMPRB, I hope. Still some lingering issues there. But for the most part, it seems that the government is more willing to work with the industry, as I said, through these life sciences strategies. And we saw a flurry of investments post-COVID, and these were really welcome. And again, a lot of them were really focused around pandemic preparedness. And in doing so, this shift, I think, in terms of economic policy, industrial policy, because I talked about that misalignment before, well, now we've seen the pendulum swing a little bit. But that also creates some issues. There's no silver bullet here, right? When policies happen, there are always consequences. And one of the consequences we're seeing now is a talent gap that's opening up over the next 10 years and an increased demand. This is from a report by BioTalent Canada. I sit on their board of directors. Fantastic report that was issued in 2021, and they predict that there's going to be a gap of about 65,000 workers in Canada over the next decade. And what they also measured was how are we doing as an industry, as a sector, in terms of diversity and inclusion. And the news is not good. We do not fare well, particularly in Indigenous populations and people with disabilities, newcomers to Canada, and even people with that are visible minorities. And we need to do better, not only to fill this talent gap, but think about it. Life sciences is an innovation industry. Everything we do is based on innovation. How can we be innovative if we're limiting the perceptions and diversities that we're engaging the people that are part of our sector? It doesn't make any sense. So we need to do better in terms of inclusion and diversity. And we've actually termed it IDEA, Inclusion, Diversity, Equity, and Accessibility. And we've worked with a number of partners. We were co-founders of something called the Inclusive Life Sciences Collaboration. And these are life sciences organizations like LSO that value the principles of IDEA and want to be champions for the principles of IDEA. We want to position life sciences as an industrial leader in diversity and inclusion. And again, we have a huge opportunity to do that. So we're working together with our partners to position life sciences in that light and make sure that we're welcoming and inclusive. There are other organizations, and I'm mentioning 3 here, that I would say are the leaders in talent development, sort of HR resources within life sciences. And this is BioTalent Canada, which I mentioned, Admare Bio Innovations, and Castle. Great organizations. They have job boards, they have wage subsidies, they have all sorts of communities of practice. So as graduates in life sciences, these are resources that I think are tremendous and available to you. I also mentioned earlier that LSO runs a scholarship program. And remember, we're fully member funded, so all of our scholarship has been through the support of our members. And this was not an initiative that started as an IDEA initiative, an inclusion and diversity initiative. But as we were doing our work in IDEA, we said, we better make sure that our scholarship doesn't have inherent bias and systemic bias in terms of how we're choosing our winners. So we better start measuring. And so we did. And what we found, I think, was very encouraging. We found that the majority of our awards, 72% of our awards actually went to women, and 70% were people that identified as visible minorities. So we're really proud of that. And over the last 4 years, we've given out 135 of these awards to the tune of $425,000. And we're continuing into our 5th year this year. So really proud of this work. All right, now the crystal ball. Where are we headed? Well, when we think about the future, we need to think about what are the drivers of change. And I think about it like a push-pull. Technology being the push and necessity being the pull. And here's a good example. How many people know when Zoom's platform was launched? Who thinks it was 2019? Let's see, show of hands. 2019? No, not too many people. How about 2017? Was Zoom launched in 2017? A few more hands. 2015? Yeah, okay. How about 2013? It was in fact 2013. So Zoom was around for nearly a decade before the pandemic hit, right? I'd never heard of it, never used it, but now we've all sort of seen and used it. It's a great example of how you had a technology available, wasn't being used, but when you needed it, wow, then everybody's used it now, right? Because there was a necessity there. So that necessity, that pull, is a big driver of innovation, whereas technology tends to be the push. Also like to think about innovation in 3 different buckets. So these are the ones that I use, is product innovation, process innovation, and policy innovation. So product innovation is kind of obvious. It's, new products, so like immunotherapies or gene therapies. Process is more how we go about doing things. AI is a good example of this. There's a great company in Ontario called Deep Genomics that uses AI in drug discovery. It's a good example of sort of process innovation. And policy innovation. Again, the pandemic was a great example of that. We had to do things differently. We had to regulate, how we approved the vaccines and found reimbursement for it. All of those were policy innovations. Now, when we think about the pull, those necessities, we can point to a few things that are fairly obvious on the horizon. We have an aging demographic here in Canada. We've got more empowered consumers. This is a really interesting one because most of us have cell phones. We have access to, our banking information all digitally, all of that. But we're still, way behind in terms of our health data, our health records. We actually had the Minister of Health from Poland speak at our AGM earlier this year. And a couple years ago, they went entirely digital. Every citizen now has on their phone access to their health records. They can communicate with their family doctors all on, no paper. It doesn't exist anymore. We still have fax machines. So way to go here. Ways to go here. Sustainability, social prosperity, pandemic preparedness, economic security, health equity is a really important one. And I think the pandemic showed that, again, there is a lot of inequity in terms of our healthcare system and needs to be addressed. Another area that I think is really interesting that I'm going to call out is what we call One Health. And One Health is the convergence of environmental health, animal health, and human health. And I think it's an interesting way when you think about all of the different elements of life sciences and how those come together and the interdependence that they have on one another. And even if you think about something like zoonotic disease, like we had seen with COVID-19, that's a very unique way. So that's one I'm keeping an eye on. The future of medicine. Here in Canada, we are really good at critical care. If you're critically wounded and you go to the emergency, they're going to fix you up, right? They're good at treating sort of critical care. We are not particularly good at preventative medicine and wellness. And I think that needs to change. I told you that life sciences is a very diverse sector, and one of the areas that we cover is agricultural technology. Me and my team had an opportunity to visit the University of Guelph. They have a research farm, a dairy farm, out in Elora, and we visited that farm, and it was fascinating. These are the most well-treated cows you have ever seen in your life. These cows are monitored 24/7. When the cows feed, their temperatures are taken, their weight is taken and recorded, the amount that they're eating and consumed is recorded. Same with when the cows are being milked, and it's a tremendous amount of data that's being collected on these animals. And the guy that was giving us the tour, he actually grew up on a dairy farm. And he said, one of his jobs growing up on the farm was identifying which cows were sick, right? Because they got to get the sick cows out of the herd so they don't infect others, etc. He says, I can spot a sick cow like that. With the data that they have, they could predict when a cow was going to be sick about 3 to 4 days in advance of it showing any symptoms. Way before this guy could see them. They say, oh, that cow's sick. No, it's not. Sure enough, it was. So imagine now if we're able to apply that technology in agriculture to ourselves. We all carry cell phones. Many of us wear, the Apple Watches or a Fitbit. There's data, like a huge amount of data that can be collected on us. So in terms of prevention and wellness, data is going to play a key role in this as well. Oops. All right, going to wrap up here. Life sciences policy innovation. Again, I talked about the strategies, really excited about those. I think we're heading down the right path. There's also a lot happening. The discussion about national pharmacare hasn't gone away. That's going to be an area that we're going to continue to monitor. There's also a federal rare disease strategy, which is fantastic, but at the end of the day, it's got to be delivered by the provinces, right? So how is that going to play out? So A lot of policy innovation actually happening in the life sciences space right now as we speak. So I started with why, I'm going to end with why. I hope you can see why I'm so passionate about the life sciences industry, and I hope I've shown you the opportunity that we have in front of us. And for all of us that are part of this industry, I hope you share that passion. We're all ambassadors of life sciences, and so you should be proud of being a part of this sector and this industry. I know that I certainly am, and I'm going to end it there and say thank you very much for your attention. I'm happy to answer any questions.
Thank you very much, Jason. As you guys think of your questions, I'm going to start us off here. We'll take about 10 minutes. I know we started a little bit late for questions for Jason. So I'm going to ask for your help here for a second, Jason.
Sure.
As someone who runs a life sciences event, I often get asked, sort of, can you define what life sciences is? And you've defined it very well by sector in your presentation today. But if someone came up to you on the street and say, what's life sciences? How would you answer that?
Yeah, it's a good question. It's a hard one to answer, but probably I would answer it the same way that I did, is that the life sciences sector is really any technology service that is rooted in life sciences, anything with a DNA, essentially. I think the easiest way, though, is giving examples like I gave. So it's everything from the pharmaceutical and med tech industry, like human health-based technologies and services, to agricultural. Again, anything living, that's the foundation that we're talking about. So that's typically how I would define it. I know that probably doesn't help, but it's the best I can do.
Anyone else? Questions? Just put up your hand. I'll bring the mic over to you.
Jason, I enjoy your talk. Thank you very much.
Thanks, John.
I invited you in I forgot when it was, to give the same talk, and you've got some of the same slides. But, you know, we're in a university. Universities are structured in traditional ways.
Yep.
You know, we've got our departments, our various fiefdoms, and so on and so forth. And yet life sciences, as you pointed out, has no boundaries. In fact, I once said that within this university, there are life science research in every single faculty. Yeah. So what can universities do about moving towards this integrated approach and understanding of the whole life sciences spectrum?
That's a great question. And first of all, let me address the old slides first. So, John, the great thing about universities is the students turn over. It's only the old guys like you that notice the same slides. Yeah, I think it's a great question, and there are regions that have done this really well. I think, and I shouldn't say just regions, I think there are organizations that have done this really well, where they take a multidisciplinary, multifaceted approach to problem solving. And I think that's really where we see life sciences sort of crossing across those, you know, academic departments, et cetera, is you're focused on a problem and bringing in multidisciplinary approaches to it. And I think organizations that do that are the ones that are successful and then really sort of achieve the full benefits and the full potential of this life sciences industry and the diversity in it. You're welcome.
More questions?
Hi, thank you for your talk. I really appreciated it, especially as a Simpsons fan. I really liked your presentation. I was wondering, to me, as a health science student, it's fairly obvious that if we fund health science research and innovation, we can improve our healthcare system and reduce our costs in the long run. Mm-hmm. So I was wondering if you think that our governments are aware of this and if they're moving towards this, or if there's any change regarding this at all.
That's a fantastic question, and that's a big question that we've been asking for a long time. It seems obvious to us, right, that operate in this space, but it's really the structures of government that are the challenge. So let me give you an example. You know, a few years back, there was a new product that was launched, a drug for hepatitis C, and it was transformational. It wasn't cheap, and a lot of people wanted it because it was essentially a cure. And the government agency that basically funds these medicines, they were upset. Like, they were really upset because the way that they're structured is that they've got a budget of this amount, right, to fund drugs in the province. And they project that every year that budget needs to grow by X%, right? So along comes this new medicine that a huge population of people with hepatitis C want, it's expensive, and all of a sudden their budget goes like that. So they've blown the budget out of the water, and they're upset because how are we going to pay for this, right? We're going to have to get money from elsewhere within the government. But what they're missing is that not only are you having all of the socioeconomic benefits of that product, but there are other areas that are impacted within the health system. So associated liver surgeries with hepatitis C drop like a stone. And there were huge cost savings. If you actually ask somebody in the Ministry of Health now about hepatitis C, they, oh yeah, that's great, we love that, right? Saved us lots of money. But at the time, it was a disaster. Because there's no mechanism in government to say, okay, the investment you're making in this budgetary area, because it's siloed, is going to cause savings in this area, and how do we do that math? It's the structures of government and health procurement that are the real challenge there. It's getting better. I think there is a recognition that there needs to be more done, but still our health procurement is really rooted in the lowest cost rather than value, impact, patient outcomes, long-term investment and return on investment. We call it value-based procurement, and that's what we're working towards. But you're changing the structures and the culture within the system, which is hard.
Maria?
Thanks so much, Jason. This is really inspiring. So again, as an academic institution, we're focused on training. You're plugged in on both ends, academic institutions and the industry folks. We're really good at training scientists, for example, to go on and do research. Mm-hmm. But are we missing some key components that are going to help them actually innovate and be a real player in the economy? So I would love to hear your thoughts on it.
Short answer is yes, and BioTalent Canada has done a really good job at articulating this. If you take a look at their labor market report, one of the things that they talk about is where there are some skills gap, particularly soft skills. We scientists, I'm going to say that because I'm one of them, generally, and again, this is a generalization, typically are not always the best communicators. Right? That's an area where I think there's a huge opportunity to develop soft skills. Interpersonal skills, being part of teams, project management. These are all skills that employers look for. Technical skills are fantastic, but the soft skills are just as important. So it's an area where I think, there needs to be probably a little bit more focus. And again, I think it's gotten better. I mean, back when I was a grad student, there was no consideration given to this, but I see now in universities and in programs that there's, more, of this business acumen being developed as well. And that's a good thing.
Okay, we'll take one more question here, and then we'll go into a break, but I'm sure Jason would be willing to sort of chat with you guys over coffee in the break here.
Hey, Jason. This is Sue Bertram, Associate Dean Science here at Carleton. Your slide about the different people that are entering into the sector, the fact that there are very few minorities, that didn't surprise me at all. Mm-hmm. But as an institution, and I think across Canada, I think we're doing a real disservice to our graduate students because we're not funding them well. Mm-hmm. If we look at the last 20 years, OGS funding, Ontario Graduate Student Funding, has not changed. It's $15,000 a year. Mm-hmm. If we look at NSERC funding, CGSD, PGSD, that hasn't changed. It's either been $21,000 a year or $35,000 a year for at least 20 years.
Sue, couldn't agree more. Thank you for the question. It's a huge challenge, and one that's playing out, I think, quite publicly as well. And we need to do more in terms of those supports. I do think that there's more to it than just the supports. That's one element of it. I think there's systemic barriers going right back to elementary school. We have to think about the journey of equity-deserving groups in order to access this sector. And I think it's very, very different than somebody with privilege that has experience. We've been doing a lot of work with an organization called Visions of Science, which is fantastic. It was started by a woman named Dr. Eugenia Duaduati, and she does a lot of work in the Scarborough community where she lived and grew up. And it was her way of she took her experience going through and gaining her PhD at U of T, and then going back to the community that she grew up in and bringing science to elementary institutions. And again, at different stages, right up through high school, because a lot of people in her community, they didn't have role models, right? They couldn't see themselves in these STEM positions. And so initiatives like that, I think, are really, really important. It has to be a multifaceted approach. There's a difference too between just diversity, but also inclusion, making sure that our sector, our industry, the different aspects of it, including our academic institutes, are aware of the needs of these equity-deserving groups and what it means to be truly inclusive. So those are areas that I think we need to do. But yes, the financial support is important. It's fundamental. So it's one of those key components that we need to address.
Great. Well, thanks so much, Jason, for taking part in this today. We really appreciate it.
Thanks, Jeff.
And we'll go for break. We'll come back for 9:30.
that can backfire. Not invested in life sciences, right? I got lots of money, none of it's going into the center. Well, Quebec's better, but I'm talking Ontario because they're operating on a different scale. No worries, pleasure.
All right, so for those folks still in the atrium, please come in and we're going to start the next session here. All right, so we're gonna kick off sort of the Carleton portion of Carleton and Ottawa centric portion of Life Sciences Day here, and to kick us off, I'm going to bring up our Dean of Science, Maria DeRosa, to say a few words of welcome to the group. So Maria, over to you.
Oh. Thanks, everybody. I want to begin. I know we had a land acknowledgement, but I think it's important just to recenter and remember that we're here on the traditional and unceded territory of the Algonquin Nation. And I think we heard a little bit earlier this morning from Jason about some opportunities and some challenges, and maybe we could be thinking about how can we do a better job training Indigenous populations in this, emerging field, and how can we make sure that the benefits of life sciences work their way back to Indigenous communities. So thanks, everybody. Again, my name is Maria DeRosa. I'm the Dean of Science here at Carleton, and I'm just delighted to be here to kick off this next portion of Life Sciences Day 6.0. Our theme this year is the celebration of the diverse and dynamic talent ecosystem we're fortunate to have here in Ottawa. So I think it's going to be a great day. There's a lot to discuss. Jason kicked us off so beautifully, getting us thinking about talent and all the opportunities that are ahead of us. So by pinpointing and connecting Ottawa's pivotal sectors of academia, industry, and government, we hope that today's event will create a fostering environment that will lead to a flourishing talent pool that will make a lasting impact in our community and in our world. So if you'll indulge me for a few minutes, I want to talk about how Carleton Science is involved, how Carleton in general and Carleton Science is involved in life sciences writ large. And I think that that large tent that you left for us about what is life science, is everything with DNA, I think that fits perfectly into what we think of life sciences here at Carleton. So life sciences is a key pillar of the Faculty of Sciences response to our strategic integrated plan. If you were here last year or virtually, I discussed a vision for Carleton to develop into a leader in training, research, and talent development in life sciences. And so I wanted to check in and give you a few updates on some meaningful steps we took to achieving that goal last year. I think it's important for us to remember in October, one of our amazing biology professors, Lenore Farrig, received the prestigious NSERC Hertzberg Gold Medal for Science and Engineering for her biodiversity work. And I think, again, that fits in that big life sciences umbrella. This award is considered Canada's top honor in science and engineering. Another notable thing that happened last summer, we extended our partnership and co-location agreement with Turnstone Biologics. This partnership helps fund grad students and postdocs across the faculty and has brought in nearly $2 million in research funding over the past 3 years. We really, really value this relationship with Turnstone, so thank you. We have created 2 new professional graduate programs that are working their way through the approvals process and will be online soon. A master's in biotechnology and a master's of clinical trials and regulatory affairs, both which should be ready to launch in the coming year. We've also partnered with BioTalent Canada to provide all Carleton graduate students and undergraduate students with free access to the BioTalent suite of essential and technical skills training programs to help prepare our students for work in the bioeconomy. Students, if you're interested, please see Ethan Hermer, who's going to raise his hand, and you can get access to these courses. In January, we officially signed on to the Canadian Partnership for Research in Immunotherapy Manufacturing Excellence, CAN-PRIME program. This program provides students with specialized training and co-op placements at the Ottawa Hospital's Biotherapeutics Manufacturing Centre. I'm proud to announce that in a competitive application process, 2 of those placements came to Carleton undergraduate students. And the last thing I think I want to note, I think I saw Leila here, Professors Adana Casal and Leila Mostako-Guidolin, who have been speakers at life sciences events in the past. They led the launch of the Tissue Engineering and Advanced Materials Team Hub, and so we're really excited to get that online and have that very state-of-the-art bioimaging, tissue, and biomaterials facility. It's a collaboration between the Faculty of Science and the Faculty of Engineering and Design. So, we're really incredibly excited about the future of life sciences here in Ottawa and the role we can play as part of the growth of the sector in the region. I definitely want to thank our partners to put on today's event, so LSO and OBIO. I want to thank Jeff Smurl for putting this event on with all the team you heard about a little bit earlier. And I want to thank John Absimon for his leadership over all the years of as we've been building this event and this kind of ecosystem here at Carleton University. So I think we've taken to heart BioTalent's report on the desperate need to train, upskill, and reskill tens of thousands of workers to help support growth in the life sciences economy. We will work closely with our friends at U Ottawa, La Cité Collégiale, and Algonquin College to help meet this need. And with the continued support and advocacy of organizations like Life Sciences Ontario, OBIO, and in collaboration with our private and public partners, we'll continue to make Ottawa the must-visit, must-see destination for research, training, talent, and development in this sector. So again, I just want to extend a warm welcome to everyone. Thank you for being here. I hope the event is a source of inspiration, knowledge, collaboration, and it propels us towards a future where our local talent can thrive and really shape life sciences. So at this time, enough from me. I really am just delighted to be able to invite Ken Lawless to the stage for our first session of the morning, the Canadian Pandemic Preparedness Hub. So Ken is the Senior Director of the Ottawa Health Innovation Hub at U Ottawa. So we'll forgive him for that. And is also the Director of the Canadian Pandemic Preparedness Hub. During his career, Ken has helped over 150 life sciences companies with incubation, partnerships, and financing, a really remarkable legacy so far. He has served on numerous private and not-for-profit boards, expert panels, task forces, and selection panels, including Vice Chair of the Health Standards Organization, HSO, and Co-Chair of Accreditation Canada. Please help me welcome to the stage Ken Lawless. Thank you so much.
Thank you. I'm also one of those wanderers, Jason, so I do wander the stage a little bit as we go forward. And Jason's talk was a really excellent segue. We didn't plan it. Maybe Jeff planned it, but we didn't plan it because we'll be talking a lot about pandemic preparedness, and we'll be talking about the federal government strategy moving forward. And Jason, the one thing that you talked about early on was mentors. Quietly, John is one of my mentors going back many, many years, and very, very much appreciate my collaboration with John over the many, many years that we've been active. Yeah, but I still owe him 2 beers. So we're going to talk about the Canadian Pandemic Preparedness Hub. And I'm just going to flip this. Now, all of us lived through the dark days of the pandemic. Many of us lost family, friends. So this is very, very personal to many of us. And I want to talk here about the 100-day mission. And the federal government basically, this is put together by the Bill and Melinda Gates Foundation that was then adopted by CP. All about we need to do better. We need to be better prepared. And we need to be better prepared both in advance of a pandemic, but also in that first 100 days. So everything we do prior to that really has to focus on being prepared now. And so when the WHO declares a public health emergency, as we saw with the pandemic, the challenge is, can we be ready in 100 days with vaccines, with therapeutics, and diagnostics at the ready to respond? That's a global challenge. That's a daunting challenge. Now, what the federal government did was they put $2.2 billion into this, into their 21 budget. $1 billion of that was really focused on large-scale commercial manufacturing through the SIF program. And so you saw in Jason's presentation, Sanofi, Resilience, Moderna, and others getting money to increase our capacity, because one of the big gaps we found is that we have no capacity in Canada to produce vaccines. But where are the vaccines going to come from? Where's that new a type of technology going to come from? Well, it comes out of universities and research institutes. So the federal government put together $1 billion to focus on this area. Now, before I jump to that, here's a little bit more on the challenge. It was absolutely amazing that we could go from 0 to a vaccine in 336 days. That saved the world. That literally saved the world. What the 100-day mission is, can we do it better? Because if we can intercede quicker, we can save a lot of lives. And we can prevent some of the huge social and economic upheaval that a pandemic really brought on us. So here's what the federal government put together in that strategy. They created the Canadian Biomedical Research Fund, about $250 million for research and training. The BRIF Fund, which is all about infrastructure, they put $500 million on the table. $150 million was already spent focusing on biocontainment lab level 3, so that we can actually work with live viruses and live pathogens. And that has already been announced. And a clinical trials fund that was put together by with CIHR. That fund has already been announced, and there is a single hub, if you want, called ACT, that was formed. And oh, by the way, who's the leadership of that? Western, McMaster, and OHRI. And so this is really important as you then start to talk about what our hub is and bringing those collaborations together. A little bit more. So in stage 1, which was started last year, they're going to choose 5 hubs across Canada, or less. They came back with 5 hubs. And they're going to give us a little bit of money to organize, about $500K a year. And with that, that brings together all the partnerships that we need to then focus on stage 2. And stage 2 really represents about $575 million of research, training, and infrastructure funding. Unprecedented in Canada. And so this is a really, really wonderful opportunity. The other hubs, there's a hub based out of Montreal. There's a hub based that's led by University of Toronto. There's a hub that's led out of University of Alberta, Prairie, and a hub led out of UBC. We are the only pan-Canadian hub. We extend from BC to Dalhousie. And I'll talk a little bit more about that. And that gives us a very interesting dynamic. We're also one of the only hubs that focuses in biomanufacturing. And so this is where we are. So let's talk about the stage 2 proposals, because that's where we really are right now. And what are we looking at? This isn't like a normal CIHR grant or an NSERC grant. These represent innovative initiatives on a larger scale and a higher risk. So this is risky. We need to be able to break the boundary and move forward. So it can be applied research in biomanufacturing, life science sector. Talent is a huge issue, and you're going to hear from Jennifer in the panel a little bit later, and of course Amora and others, about how important that talent requirement is for this industry moving forward. And of course, critical to this is the research infrastructure. So this is the stage 2 funds that each hub now is adjudicating through an EOI process, which then will move to a notice of intent process in early June, and then final application in September. We'll talk a bit about more. So what is CP2H, Canadian Pandemic Preparedness Hub, really all about? Well, our aim is to solve a fundamental problem hindering patient access to Canadian discoveries and commercialization. And so what's all this about? Well, the valley of death. We have the valley of death in financing, but we also have a valley of death in terms of getting a discovery across to the clinic. And this is where we're focused on discovery translation, biomanufacturing, and the enabling studies. These enabling studies allow you to put together your regulatory packages for clinical trial development. And so this is a recognized gap. We're very, very focused in this space. So who are we? Well, we're 48 different partners, co-led with McMaster University and here in Ottawa, the University of Ottawa and the Ottawa Hospital Research Institute. We have multiple universities and colleges, including Carleton University, La Cité, Algonquin, but also Mohawk, University of Alberta, University of Saskatchewan, and others. We have great partners like BioCanRx and CanPrime, and people like Castle, and of course, here in Ottawa, led here in Ottawa, Covarnet, which was run by Marc-André Langlois, which basically identified and mapped all of the COVID variants and how we had to change our vaccines as each of those variants came along, and provided advice to the federal government. So what are we all about? Well, we're going to transform research and clinical manufacturing pipelines so that Canada can pivot quickly, that 100-day challenge, to manufacture vaccines, therapeutics, and diagnostics. How are we going to do that? We're going to expand research and GMP manufacturing infrastructure and talent investments. We're going to accelerate translation of our novel platforms and technologies into commercialization by providing that bridge. We're going to coordinate and develop experiential training programs. And then finally, we're going to support the development of all those small and medium-sized enterprises that Canada is so great at starting, but then have difficulty crossing that valley of death. And we'll do that through the programs and the research activities of the hub. This is the team. Our executive board is chaired by Karen Mossman, who's the VP of Research and Innovation at McMaster, and Sylvain Charbonneau, my boss. I have to put him up there, just my boss, you know, just have to do that. And our two scientific co-leads are Matt Miller out of McMaster. Matt is a recognized, world-recognized virologist. Matter of fact, he just was invited to go talk to folks in Sweden, the Nobel Committee about vaccine development and mucosal vaccine, so a new way of delivering vaccines through the nose. And John Bell, most of you know John, who has been involved with cancer research for a very long time, but also is one of the key people running the biomanufacturing center at the Ottawa Hospital. And we've tapped into leadership across the entire country. And you'll note what we've done looking at ECR, early career, as we matched in each of our pillars, we've matched an early career researcher with a seasoned veteran, and they're working together on all of our programs. So what's our strategic areas of focus? Obviously, biomanufacturing. We've built a Trans-Canadian Biomanufacturing Cooperative, which I'll talk about. We're building these high-performing translational research and development teams. Almost all of our researchers have brought a vaccine or an antiviral to the marketplace, past clinical trials. We're also doing training, and we have a network of regional experiential HDP training centers that we will be populating across the country. We're going to support those SMEs to cross that valley of death, and we're going to be looking at pandemic preparedness in a very different way. We're going to look at biannual readiness exercises. We're going to work with Calian in Ottawa, who have developed software that will allow us to actually map and run exercises on, are we prepared? Is our biomanufacturing ecosystem prepared and ready to meet the 100-day challenge? And then we're going to test it and see if we can do that with some of our products that are coming through the pipeline. We've built five platforms: viral vectors, biotherapeutic innovations, small molecules, which are really focused on antimicrobials and antiviral therapies. We also want to have a platform really focused on scalable biomanufacturing. It's maybe great to have a process, but if you can't scale that quickly into a manufacturing process, that the regulators are happy with, you're dead in the water. And then finally, a diagnostics and clinical assays focus, and I'll get back to those in a moment. And one of the things that we've also introduced is a cross-cutting platform on social science strategies. All of this to start to take those novel products and therapeutics and vaccines and treatments that we have and get them across that valley of death. And to do that in a concerted and focused way. We also have built a collaborative across our hub in manufacturing. We can do end-to-end today, end-to-end phase 1 through phase 3 capacity. And that includes the Ottawa Hospitals BMC, McMaster's Fitzhenry Lab, Vito in Saskatchewan, and the University of Alberta's cell therapy manufacturing. We've brought them together. We're going to be cross-training. We're going to be looking at procurement together. This is already something that we already have. And what we'll be doing is then making investments in those facilities, and in particular for CP2H, new investments in the Biomanufacturing Centre in Ottawa and new investments in the Fitzhenry. This is going to add the capacity that we need in order to be able to handle infectious diseases, pandemics, and others as we move forward. So I'm going to go briefly through these. These are eye charts for most of you. First platform on really focuses on viral vectors and vaccines. And what we're about is to try to take this portfolio of vaccine technologies and be able to bring them across that valley of death and be able to create those regulatory packages that allow for rapid assessment. The reason why mRNA was so successful, why? Because it was being developed as a cancer vaccine. The regulators already had experience with it, and so it was able to move quickly into phase 1, relatively. Now we want to speed that up and move forward. The second platform focuses on antivirals, and what we're trying to do here is to de-risk a panel of anti-infective drug leads to high priority bacterial, fungal, and viral pathogens. So it's not just about vaccines, it's about treating with antivirals as well. And so this is what this platform is all about, and it'll include as well building access to GMP manufacturing for these small molecules, another infrastructure that's needed in Canada to support that. We also have the scalable biomanufacturing innovations, and as I've told you, this is really about how we take those processes and scale them. Because it's one thing to be able to do it at a phase 1 scale, it's another thing to do it at a commercial scale. And so we have to be able to do that. Same thing in diagnostics, we're looking at point of care. All of you have had those strips and everything else, but that's one test. Now, can we be able to create point of care tests that are, we're able to test not only for COVID, but for flu, for other pathogens, so that when you come in with a fever, you actually know what it is you have and not, well, I'm guessing, well, maybe it's COVID, well, it hasn't arrived yet. And so it's this next generation of tests for that. The social sciences is really, really important here. We all witnessed vaccine hesitancy. Oh, I don't want to get a vaccine, it's too new. Oh, it's not, right? But there's also other barriers here. Can we produce that new vaccine in an economic way that we can actually get it to the world? So we'll be doing health technology assessments and providing that service to all of those products that we're building out as we're going forward, plus doing research in that space. So this is something that's unique that we'll be building into our platforms. And then finally, it's really about training. So we're bringing and working together with BioKinRx and the CanPrime program. We're working with Jennifer and her team. We're working with Castle, really trying to focus on the biomanufacturing skills that are needed. You, as students, may have all the great skills that you have in terms of fundamental research, but we can't let you into a GMP manufacturing center. Why? Because you haven't been certified. So we're trying to build again, eliminate that gap and trying to make that at both, not just a regional level, which we can do here in Ottawa, but at a national level through the programs that we have. So what are the timelines? Well, in March, they announced stage 2. Coming up in 2 short weeks, June 8th, all the proponents will then have their opportunity to submit a notice of intent. And if they don't submit a notice of intent, they can't do a final application. We've introduced in front of this an expression of interest, because in the end, the only way that you can actually put a full application is you have to have the endorsement of a hub. So what we're doing is we're triaging before the NOI, we'll triage after the NOI so we can bundle and get the very best proposals that'll have an impact and drive those forward. And so this is our process going forward. So I can tell you that we've gone through our EOI process. And so we have over 65 EOIs, unprecedented. We're one of 5 hubs. You can imagine the demand on the research funds, $215 million of research funds and $360 million of infrastructure funds. As 5 hubs, we're many times multiple of that. So it creates a very, very important competition. Why? Because only the best will survive. And the best are what we need. And so this is why the process that we've gone through and are doing it, and we're doing that with our colleagues in the 4 other hubs. So we are collaborating, we're looking at hub-to-hub sharing of information, and then post the awards, how we work together as hubs to help manage our pandemic preparedness, starting from surveillance all the way through to manufacturing, and how do we get there. So this is not just an Ottawa thing, it's not just an Ontario thing, it's a pan-Canadian thing. And we're linking those other hubs that are regionally focused in this space. So this slide is just here to reemphasize that, CP2H, we have 48 partners, including 22 private sector partners. We now know that that number will probably reach 30 or 35 based on what we're seeing in the NOIs. So industry plays a very, very important role, not only in the research proposals, but also the infrastructure, and as importantly, the talent development. But they're also there to help us cross that bridge. Some of the larger companies are there, will be supporting products that have gone through that phase 1 process to large-scale manufacturing. That's why they want to be there. Others can contribute their research and their knowledge into each of those platforms and products in those platforms. So this is really a holistic approach to how we then cross that bridge together. Now, note here that if you just took that money and divided it by 5, you can see it's about 43 million per hub for the research side, and it's about, just for the infrastructure, about 55 million. So the way the program is set up, that's a sliding scale. So if programs that are being delivered by CP2H have more merit, those numbers will slide up. Somebody else may not. So this is the competition piece that we're involved in. So typically we would be thinking on infrastructure somewhere between 55 and 70 million for our hub, because it is infrastructure intensive to put manufacturing and that manufacturing space together. And so that's really, really important as we move through. And I'll stop there, and we're open to questions and discussion.
Thank you very much, Ken. That was exciting times for Ottawa and for Canada with all the investments in this sector. So we're open for questions. I'm going to start while you all think of your questions, because I'm sure you all have some great ones. You talked about training, and it's a lot of focused on sort of the skills in biomanufacturing. We also talked a little bit about social sciences and the cross-cutting strategy of that. So can you talk a little bit about the role you think training our students in science communication and the importance that that might play in terms of being ready for the next pandemic, not just in how we create research results and create new therapies, but how we present those to the general public? Because I think that was a big problem in the last one.
It's a huge issue to deal with. Probably a backbreaker type of issue for us. The way we communicate traditionally as scientists is one to another. But sometimes we have to gauge, and I talk to my 91-year-old mother and say, "What do you do?" Right? So we have to really, really think about how we communicate this, how we communicate the rigor of the science that's associated with this. A lot of the hesitancy was about the fastness, how fast those vaccines were developed, and people not understanding the systems and balances of checks. So we have, working with folks like LSO and the broader community, we have to be able to do that. But we need people who are steeped in the knowledge of these technologies to be able to communicate them well. And so as graduate students, you're going to be, and students, you're going to have to really think about in the future, not just for pandemic preparedness, but in your whole career, why would I invest in you? That's what our companies get, but it's the same thing for research and research projects. So why would I invest in you? Have you put together the complement of people necessary and the programs, and are you able to communicate that appropriately? Are you able to look at EDI, which is really, really important for these training programs? So we need to be able to do that as well. But the way we communicate is really something that I think we have to step up.
More questions?
So I actually have a bit of a follow-up question on that. As we move further away from the pandemic, how do we continue to convince the public that this is something that we need to invest in, and that it's not something that's gone, but it's something that we need to keep preparing for? And by the way, I should have said great talk.
Thank you. This is really, really important because we have the government's interest now, as Jason would say, but it's fading. We have all of your interest now, but do we have your friends and family's interest? Oh, it's behind us now. I think one of the important things that the pandemic has taught us is that the next one is coming, regardless. That's not to be, and we're being prepared for it. So it transcends a lot of the of how we communicate again, this whole piece. But it's awful nice to know that we're at least better prepared than we were previously. Those task forces that were set up for vaccine development, that took 3 months, almost 4 months to set up, because the bureaucracy isn't used to moving that forward fast. One of the unique things that happened with the pandemic was the regulatory agencies changed how they regulate these products. And so what they did was then doing rolling submissions so that they could actually keep ahead and keep track of this. So nothing like a disaster really focuses the mind more, but at the same time, we have to make sure that that you still understand that the next one is a monkeypox. Is it a new version of avian flu, a new version of SARS? Is it a new bacterium that is antibiotic resistant? These are all, or a variant of Ebola that we haven't seen before. So surveillance is really important on the front end, and I think we have that. We need to be able to plan for those eventualities and have at the ready. The platforms are plug and play, so we can drive the new sequence in and have those platforms ready to grow. And that, I think, is reassuring, but we need to be able to communicate that message. That answer question?
Ken, yeah, thanks a lot for bringing us through all that. It's really interesting, and again, congratulations for pulling this together with you and your team and making a cross-country effort, because, of course, that's what it's going to take to be prepared. You know, it struck me that you explained very well how we're going to get grassroots new innovation up through this machine to get it to available to us in the manufacturing front. What I wasn't clear on is how you can take existing inventions, existing innovations that are already in the ecosystem, companies that have expertise, people that have expertise in this that aren't embedded in this mechanism and aren't in the university system, for example, and fold that opportunity into this mechanism. If you're truly trying to get the best available for the for Canadians and for this outcome, what's the interface with industry?
So very, very good and excellent question. So first of all, that the interface is, we're seeing it in the EOIs as companies are stepping up in these research proposals that are coming forward in the context of they have platforms that we can be testing and developing. Verica would be an example, and others that we have locally. We also have companies also are interested in the talent that can be developed here, and so we're seeing companies stepping up, and they'll step up again after these proposals have been through. We will be able to then encourage more industrial collaboration beyond what CBRF can provide. So the training program and funding that CBRF can provide is only foundational. What we need will be industry coming to the table, along with other government programs, both provincially and federally, to scale. It's all about scaling, but we got to get the foundation right. So that's part of it. The other part of it is the skills that those companies bring and the expertise. We can see opportunities where they will contract into these facilities, the manufacturing facilities, to be able to manufacture their own product, but also then be embedded in those facilities to support the translation of that knowledge. And every time you do that, there's more knowledge that then is brought into those academic manufacturing centers in the context of how to approach the problem, how to approach the regulatory side and do it. So there's many, many ways. Obviously, money is one support mechanism, and we've had a significant amount of both dollars and in kind pledged to CP2H. But understand that what we're going through here is about getting ourselves prepared for that. But the hub is active for the next 4 years and probably will be funded for another 4 years thereafter. It's how we bring the ecosystem together, how we look at challenges. A really, really important lesson of the pandemic was supply chain. Huge issues with supply chain. Borders suddenly close. So we're working with industry looking at how we address supply chain issues. We're working with the biomanufacturing centers that are involved with us, including NRC, in terms of how common procurement practices so that we can actually have stocks of all things, bags that you use in a bioreactor available, because there's a 2-year waiting list for it. And you can't get it across the border because it's a strategic product that one country will not let you borrow. So this interface is only the beginning of the interaction. It's not the end. So we will be looking at doing it. And the final thing is that we will have industry supporting these projects going through and advising on the best path to move forward. And we're working with Obio on that as well in terms of the commercialization of those novel, new, or those existing that need to cross that bridge and how to cross that bridge fast and effectively. And by the way, we're set up with the clinical trial people here, waiting for those products to come forward, so we can expedite across that whole spectrum. But that's basically how we do it.
So we'll take one more question. I think David had it over here, and then we'll go to break. But please, Ken, if you wouldn't mind sort of chatting with folks in the break, that would be great.
Thank you for giving us a very nice overview of all this. I'm wondering if you can provide a little bit more information, a broad overview as well, as to what goes into the evaluation criteria for selecting
Boy, oh boy.
meritorious proposals.
So if you go to the CBRF website, you'll see all the evaluation criteria that are there. Effectively, it's about discussions with deputy ministers and others. It's not about just doing basic science and having that. It's about how we translate that science, how we engage and involve industry, and then how we then bring the talent to bear. So there are up to 16 different criteria that each of those will be judged upon. If you just do infrastructure, it's less. If you just do research, it's less. But if you put together a proposal that has research, infrastructure, and training, you now have 16 different criteria that they're looking at. So we were successful in becoming a hub because we knew and identified those gaps and how we could fill those gaps, and the criteria that we're measuring those against the criteria that the funding agencies have put out. And so there is a strategic review committee that will be looking at every one of those proposals. They'll also be looking at our portfolio of proposals that we're endorsing and seeing, these guys, have they got it right? Have they got the right mix? Are they committed to doing this? So this is multi-tiered. And then that steps itself up, and I didn't put the slide in, but it steps itself up to the ministerial level as well. Is it meeting the biomanufacturing and life sciences strategy? Is it supporting our life science industry? Is it supporting our ecosystem? So this is not just and I don't say just, it's not a CIHR grant or an insert grant. It's a series of institutional grants that are brought together under a hub in order to do it. But that's the way the criteria is. But if you're interested in the criteria, just type CBRF and you'll see all the criteria that we have to be able to do. And it's burdensome, but it's very, very important because it'll bring out the best aspects of those proposals that we have to deliver on.
Okay, please join me in thanking Ken again for a fantastic talk. We'll be back here at 10:30 for the final two sessions. They're back to back of the final two speaking sessions, and then we'll move into the lunch and the poster session. So thank you.
I even mentioned you.
Yeah, another publication.
So Ken, I've got a good one for you that I heard.
To everyone out in the atrium, we're going to get started with the next session, please. So if you wouldn't mind making your way back in, that would be great.
Good. So, all right. So just yeah, Corrine Millard. Okay. Menno Udolf. Okay. All right. Allison Brady. David Sabatini. Okay. Good. Yeah, exactly. Yeah. So it's going well, right? Yeah. You were hoping for more people, or?
Yeah. It's online too, so
Yeah.
I don't know how many people.
Right. Oh, online.
Yeah.
Okay. So I'm not making any appropriate jokes.
You want to walk around, so for the question, there's only going to be time for a couple questions for each one.
Okay.
But if you want to just use this, just make sure you turn it on.
Okay.
And you can feed the questions.
Okay.
To,
Sounds good.
to Brad, right?
So is this the order they're going to go in?
Yep. So it's Allison, David, Corrine, Menno.
Okay. Okay. All right.
So yeah, if you want to stand, I'll just welcome
Okay.
everybody back. And
All right.
I'll introduce you. All right, we're gonna start again here. Welcome back, everyone. I do have one quick announcement. If somebody lost their Presto card, it was found on the floor. Come find me. I have it in my pocket, and yeah, you don't want to lose that. So our next session is going to be introducing some newer faculty members here at Carleton and introducing their research programs. So to moderate this session, I'd like to welcome our Associate Dean Research within the Faculty of Science, Dr. Jit Bose, to run the session. So Jit, over to you.
All right. Hi, everybody. My name is Prosenjit Bose, but you can call me Jit. Actually, nobody calls me Prosenjit, except for my mom when she's angry with me. So I prefer you call me Jit. So I'm the Associate Dean of Research at Carleton in the Faculty of Science, and I'm pleased to moderate this session. It's going to be a really cool session. We have 4 of our researchers who are going to be giving you a brief overview of their research area. So let me introduce the first speaker. The first speaker is Allison Brady. Allison is an assistant professor in the Department of Biology. She got her PhD in Earth Science from the University of McMaster, sorry. So I was reading through your bio, and really cool stuff. I think you guys are going to be amazed. I mean, she's worked with NASA and is looking for the existence of life in harsh environments and so on. So sounds really cool. So I think I will let you tell us about all these cool things. All right.
I understand there's a slide clicker up here, so please bear with me for a second. Okay, thank you for that introduction. Can you guys hear me? Is my wireless mic working? I wander away from that mic. Does it? Yes, some people are nodding, some people are shaking their heads. All right. All right, so let's see if this is going to work. What do I point at? There we go. I would like you to just take a second and think about microbiology. What is the first word, or maybe the first couple of ideas that come to mind when you hear the word microbiology, microorganisms? What do you think about? And I would guess that the majority of you think about things related to human health. So thinking about diseases, about viruses, maybe about antibiotic resistance. Or maybe you're thinking about food microbiology and how important microorganisms can be with respect to making things like cheese, beer, wine. But also, I bet quite a few of you have probably encountered something in your fridge. You pull it out, you don't know what it used to be. This is food microbiology. But at the same time, microorganisms are exceptionally important, and they exist all around us. They exist in the environment. They exist in the soil, in the air, in the water. And environmental microbiology is really critically important for cycling a lot of important things like carbon, like nitrogen. But it's often overlooked in a lot of ecosystems. But microorganisms for billions of years have actually been influencing the Earth, the physical shape of the Earth, the mineralogical components, the chemistry for billions of years. But the reality is we don't know a lot about these microorganisms. There we go. So just to tell you a little bit more about myself, my background is microbiology and earth sciences. Yes, I did come from an earth sciences department at McMaster. But that's because really I've been interested in this question of what are microorganisms doing in the environment. And I have been very fortunate to be able to have gone to a lot of really cool locations to have worked on this and try to answer these questions. And I draw on both microbiology and earth sciences analytical tools to try to answer this question. And again, for most of the species, the microbial species that exist on Earth, we don't really know what they do. And yet these are really the unseen majority. When you think about the amount of biomass on Earth, if you take away things like terrestrial plants, microorganisms make up the bulk of the biomass. And in many ecosystems, they are the dominant life form, the deep subsurface, the oceans. And again, we don't know what a lot of them do. We're really good at understanding what ones in our bodies do, but most of these environmental microorganisms, we just simply can't grow them. So we don't know what their roles are in ecosystems, but we know they're important. And we also know that there is a huge potential for discovering unique enzymes and unique metabolic capabilities. So this is where my research program comes in. There's 3 research themes that I'd like to talk to you about today. And this interdisciplinary background that I have, this drawing on geology and biology and the analytical tools, is really what I use to inform my research program in geobiology. So the 3 themes that I'm going to talk to you about just briefly today are microbial ecology, and really answering fundamental questions about what microorganisms are there and what they're doing. The second component is more applied research. So thinking about biotechnology and bioremediation. How do we use these microorganisms to help us address pressing environmental needs? And the last part is thinking about more big picture questions. Are we alone in the universe? And can we look for signs of life and understand what to look for if that life is no longer there? So the first one I'm going to talk about is just thinking about this idea of going to some of these environments and trying to understand what these microbes are doing. And as I said, even though microorganisms make up a huge component of biomass on Earth, we can't culture most of them. We can culture a lot of the ones that are associated with our bodies. We're really good at that. But a lot of these ones that live in these extreme environments, we just simply can't get them to grow. And this is a huge problem for biology because if we can't grow them, we can't understand what are their metabolic capabilities, what are their growth conditions that they need, and really trying to fit them into what their ecological roles are in a lot of these ecosystems. So I go to environments like this, like a hot spring, and looking at this image here, all of that colored material in the front is gooey microbial mat. It's all microorganisms. And they're living off of nutrients, things like methane, gases that are brought up from the deep subsurface, and they're living off of this in this microbial-dominated system. And I go to this system, and I use this combination of the earth sciences and the biological tools to try to characterize what microbes are there without having to grow them. So looking at cellular components that they produce to try to see how abundant microorganisms are. Looking at the chemical signatures of these microbial components tells me a little bit about what do they use for a carbon source. All without having to run into that challenge of how do you grow something that, as I said, for the vast majority, we just don't know how to do it. And you can also think about other systems, complete opposites. Looking at these extremes of life. We don't know, what are the extremes of life? How hot can something grow? How cold can something grow? So going to the opposite end of the Earth and looking at the Antarctic and thinking about, are there microbes here living completely isolated from the surface? And there are. Sometimes you just can't see them. But there are microorganisms living at the bottom of some of these lakes, and they are performing biogeochemical cycling, and they're developing an ecosystem completely separated from the surface. And when you start to look at some of these, there we go. And when you start to look at some of these ecosystems, you really start to see that these microorganisms have very unique capabilities, unexplored capabilities. And you can start to think about how this fits into my second research theme, which is biotechnology development. And when you think about this, microorganisms have the ability to help us address really pressing environmental concerns. So helping us to develop things like biofuels. For a lot of pollutants that we humans release into the environment, there's microorganisms that can eat them. To them, it's just another carbon source. And when you start to look at these extreme environments, you can really start to tease out how we can apply these to help us clean the air, clean the water, in a relatively easy and low-cost manner. So this is thinking about them with respect to biotechnology. And being able to reclaim land that's been used for things like oil sands tailing, or oil sands processing, and looking at the waste produced, oil sands tailings and tailings ponds. I've been involved for quite a few years in projects related to this, and at Carleton I'm going to continue working with this through a recently awarded NSERC Alliance grant, where I'm going to be looking at methane cycling in these tailings ponds. So trying to understand the microbial role in methane production and methane consumption with industry partners in the oil sands, because they're very much interested in how do they mitigate this? How do they keep these emissions from escaping? And how can they remediate this land to bring it back into a usable form? I'm also interested in pursuing a new avenue of research for me, which is microbial degradation of microplastics. So plastics are everywhere. It's a huge area of global concern. The government of Canada has tried to reduce how much plastic gets into the environment by doing things like banning single-use plastics. So you'll notice there's no longer straws. There's no longer plastic bags at the grocery store. That really helps with reduce how much waste gets into the environment. But what do we do with the plastic that's already there? And this is, again, thinking about the capabilities of these microorganisms. We know that there are microbes that can break down plastic. Again, to them, it's just another carbon source. It's another kind of hamburger. And they can eat this plastic. But we don't know a lot about what helps them do this. Are there environmental controls on this? Are there some kinds of plastic that are easier to degrade than others? And so I'm very much interested in pursuing this because plastics are everywhere. They're in the Ottawa River. They're in the Great Lakes. And so I'm going to use this combination of looking at chemical components that the microbes produce, their chemical signatures, to try to track whether or not there are microorganisms already in the environment breaking down these plastics. So let's skip to more of this big picture question. Are we alone in the universe? So imagine for a minute that you're an astronaut and you've been sent to Mars. And you've been given the objective of you get to pick one rock, maybe two rocks, if you're lucky. And you're going to bring that rock back to Earth. And this rock is going to be used to answer very fundamental questions of are we alone in the universe? How do you pick that rock? How do you decide rock A is better than rock B? And this is not Mars. This is Hawaii. And we actually can't answer this question on Earth. It's still very much debated, when did life arise on Earth? We have a hard time answering this question, and yet we know there's life on Earth. We know where there's life on Earth. Some of this has to do with scale. Those are people. So this is a lava flow in Hawaii. So just think about the scale that exists on another planet. And you're trying to make a decision about do you have that little piece of lava or that little piece of lava? Because even though an area might be habitable, does not mean it was ever inhabited. The life might not be in that rock, but maybe it's in that rock. So how do you make that kind of decision? And NASA wants to send people to Mars. They're going to do this. They're planning on doing this in the next decade or so. Kind of changes. And if anybody saw the movie The Martian, you might remember there were a lot of challenges with him going out in his spacesuit. You only have so much battery power. You only have so much oxygen. You might only be able to go out and do one of these extravehicular activities for a few hours. And just to give you a little bit of context, the Martian rover Curiosity, it's been on Mars for 10 years. It has traveled about 29 kilometers. The circumference of Mars is about 21,000 kilometers. It has not gone very far. So you're not really going to have, in 4 or 5 hours, the ability to explore the entire planet. So where you get dropped off is critically important. And this is where we start to think about finding this evidence for life on Earth, because bacteria are really, really tiny. Or sorry, evidence for life on another planet. Bacteria are really, really tiny. I really like this image because you can see on the far right is a human hair. And if you look way down on the far left, there are some microorganisms. Just highlighting how incredibly tiny these are. So you're not going to go to Mars and you're not going to see a building, a car. You're not going to see the microorganisms. And especially if those microorganisms have been dead for billions of years. What do you look for? So this is where a lot of my astrobiology research comes into play, which is looking at these analog environments, going to these extreme environments, and trying to understand what microorganisms are there, but also what do they make and what do they leave behind? What are the limits of life? So going to things like the subsurface, mining environments, the Antarctic, other extreme environments on Earth, trying to answer these kinds of questions. And I do this by looking at these organic compounds. So microorganisms might be long gone, but a lot of their cellular components, the fats they make in their cells, can be preserved over very long timescales, geologic timescales. And even though you can't see those, what you can see sometimes are things like different morphologies, different shapes of rocks, maybe different minerals that we know can be better at preserving some of these organic compounds. And those you can see from orbit, or you can see with a handheld device. So it's trying to understand what are the tools that we need to find the places that are going to be most likely to have that evidence of life, even if you need to do more analyses once you pick up that rock. So this is really trying to help those astronauts make that decision about are you picking rock A or rock B. And with that, I'll just say thank you very much for your attention today, and please come visit me in the Nesbitt building. Thank you.
Okay, all right. So we have maybe time for 1 or 2 questions. Anyone have any questions?
Thank you. That's really cool stuff. Very nice work. So the microbes and plastics. So there's, of course, scientific exploration, trying to figure out, all the conditions that these microbes will eat plastics. But at what point do you say it's good enough? Let's just get them out there, start chewing up plastics, because that's moving faster than we are.
Yes.
So from your point of view, pardon me, from your point of view, do you see that we can get there like within the next month or year?
So the work that I'm doing is finding the ones that are already doing it. So it's not necessarily taking some and putting them out there. It's doing this bioprospecting of finding microbes that are already in the environment doing this process. And so then thinking about the fact that they're already doing it, maybe there's one particular plastic they're better suited for, maybe there's an environmental condition that makes them do it better, faster, stronger, and then taking that knowledge and applying it to another environment. So this is very much the exploratory component of that. But you're right, it is moving very, very quickly. There's a lot of plastic out there, absolutely. But this is very fundamental exploration of which microbes are performing this process already. Yeah.
Any other questions? So I have one quick question. Mm-hmm. So this is a follow-up to what Matt asked. So do you look at, like, for example, these microbes that are chewing up plastics, whether they have negative effects in the sense that, maybe they'll start chewing up other stuff that they shouldn't,
Well, I mean, the microbes are going to eat, they're kind of opportunistic, right? So they'll eat up anything. And as I said, these are ones that are already doing it in the environment. And so the plastics are already there, the microbes are already there. It's more a question of, are they choosing to eat the plastic versus some other carbon source that's potentially available? And if you ideally want them to eat the plastic, how do you get them to switch from this carbon source over to that plastic one? Okay. And trying to figure that out. Are there negative components? You could argue that they're breaking it down even smaller, potentially, and so that might affect the transport of some of these plastics. But this is already happening in the environment. And so it's more just trying to track and answer some of those kinds of questions. Yeah.
Okay. All right. Well, thank you very much.
Okay. Thank you.
All All right, so our next speaker is David Sabatino. David did his PhD at McGill in the area of nucleic acid biochemistry, and then toured around the US for a while until he saw the light and came to Carleton very recently. So I will let David tell you about his research. Yeah.
Thank you very much for the kind introduction. It's a pleasure to be here today and to have the opportunity to give you a broad overview of our research program that's really been dedicated over the course of the last decade to cancer research, developing research projects and new collaborative initiatives at the interface of both chemistry and biology. So cancer research and human wellness is at the heart of the sustainability and wellness programs here at Carleton University because it forms fundamental pillars of our strategic integrated plan at developing new innovations, diagnostics, and therapeutic agents that can be used to preserve human and ecosystem health. In fact, these pillars are not only key and integrated within our university, but also within our departmental research programs, focusing in on chemistry, developing and designing new molecules and materials that can be used for sustainability research applications, as well as being dedicated to preserving human and ecosystem health, also form fundamental components of our departmental values in maintaining our strategic plan and developing new and innovative research applications for sustaining human health and human well-being. And in spite of the COVID-19 pandemic, cancer remains the leading cause of death here in Canada. So it's a national research priority when it comes to mitigating devastating morbid human diseases. In fact, just last year, over 250,000 cancer cases were diagnosed here in Canada, and over 85,000 Canadians succumbed to the disease. In fact, there's just a handful of tumors, lung being the deadliest, that account for the most majority of diagnosed cases among Canadians, including side effects that stem from non-selective and non-efficient therapeutic strategies such as chemo and radiation therapy, spinning and resulting in the innovation of new cancer therapeutic and diagnostic agents to overcome some of these limitations. And over the course of the last few years, there have been new improvements in preventative diagnosis and preventative treatment of cancer in order to improve the survival outcome, even of some of the most deadliest tumors. In fact, cancer research is interdisciplinary and it's also collaborative. It brings different fields of natural sciences and health sciences together. And our research mission has been focused on bringing together both chemistry and biology, using chemistry to be able to design and build new synthetic molecules that can be used as molecular therapeutics to probe important biological pathways that are implicated in preserving human health and well-being, as well as gaining a better understanding of cancer biology to develop new important molecular therapeutics and diagnostic agents towards them. In fact, cancer research is interdisciplinary. It combines together multiple subject matters in the health and natural sciences. It's also applying different fields together. Chemistry to design and develop new chemical tools that can probe important biological pathways to help maintain human health and to allow us to innovate new molecular diagnostic and therapeutic agents that can be used to combat a wide range of diseases, and with our personal focus being based on cancer. Cancer research is collaborative, as I've mentioned. It brings together multiple disciplines, multiple levels of expertises, ranging from the natural sciences, computational biology, computational chemistry, to help with the rational design and selection of a vast array of molecules, to identify potential leads that can be developed and manufactured by chemical synthesis using synthetic tools to make molecules. And these molecules can then be used to probe important biological pathways, either in cell or in tissue-based model, combining a series of in vitro and ex vivo-based experiments to help validate a lead that can then be translated into in vivo applications, and that can then facilitate the translation from preclinical to clinical applications to help save human lives with the innovation of new and improved molecular therapeutics. Our research program, spanning over a decade, has focused on cancer research, fundamentally in two main research areas. The first related to RNA synthetic biology for applications based on cancer gene therapy. And we've developed a multitude of different research projects in support of this important research theme. We've also pivoted to research based on peptide chemical biology for applications that are based on cancer gene therapy, but also with a special focus on cancer immunotherapy applications. And we've developed a series of different research projects in this area as well. So our research mission in the area of RNA synthetic biology is to use RNA chemistry and biology to gain a better understanding of the functional roles of RNA in governing key biological processes. Most importantly, we're interested in using synthetic RNAs to help regulate malignant gene expression, one related to oncogene expression, for potentially developing new gene therapeutics. But unfortunately, Mother Nature never designed RNA to be used as a gene therapeutic or as a drug-like molecule. There's certain inherent limitations for Mother Nature to being able to do so. But fortunately for synthetic or medicinal chemists, RNA does contain a vast array of functionality that can be fine-tuned and optimized by chemical synthesis to improve the structure-function relationships of RNA and to help convert a naturally occurring biological molecule into a therapeutic agent. Our biological targets related to cancer therapy applications are based on the glucose-regulated family of chaperone proteins that are expressed in all or many cell types, functioning primarily in assisting in protein misfolding events, either under conditions of physiological or pathologically induced stress. The GRPs have a multitude of different functionalities. In fact, in cancer, the GRPs are overexpressed, and in certain cases, they're presented on the cell surface, where they function as signaling hubs, triggering tumor initiation, proliferation, metastatic spread, and even drug treatment resistance. In fact, the GRPs have been found to be overexpressed in a wide panel of both solid and hematological malignancies, making them clinically relevant biological markers for developing precision oncology strategies for tumor-targeted diagnosis and treatment intervention strategies. One of our gene therapy applications, among others, is related to the RNA interference mechanism for suppressing malignant oncogene expression. In this gene therapy intervention strategy, short synthetic double-stranded RNA, coined as siRNA, can be combined with a delivery agent, referred to as a transfection reagent, enabling cell uptake, RNA release, where it is then recruited by a protein complex referred to as RISC. RISC binds to this double-stranded RNA scaffold, eliminates one of the two strands, and leaves behind a single-stranded RNA molecule that has Watson-Crick base pairing fidelity that can serve to recruit and hybridize to a complementary messenger RNA sequence. In our case, the oncogenic GRP messenger RNA, and function to shut down protein translation. Moreover, RISC does have RNA degrading capabilities, so it degrades that messenger RNA strand, virtually eliminating any possibility for that oncogene to be expressed into oncoproteins and for oncoproteins to then solicit tumor biology. In spite of its potential therapeutic, there are certain inherent limitations that are associated with RNAs. And over the course of the last decade, we've developed a series of different research projects that may help improve the drug-like characteristics of therapeutic RNAs. We've designed and developed new and improved synthetic RNA scaffolds based on these branch RNA templates that can self-assemble into these unique, higher-ordered RNA nanostructures that can incorporate multiple siRNAs that can target multiple oncogenes in synergy, potentially shutting down an entire cancer biology pathway to eliminate treatment resistance and to trigger new and improved anti-cancer activity. We've also designed and developed RNA bioconjugates that can combine the gene therapy utility of our double-stranded RNAs with the anti-cancer activity of some biologically active cargo, once again to potentiate the cancer cell death response. And we've also innovated new and improved RNA nanoparticles that can enable direct cell delivery and shutting down cellular pathways in tumor cells, resulting in potent anti-cancer responses. And our current and future research directions here at Carleton University builds upon these research themes in developing cancer-targeted gene therapy approaches to target and kill cancer cells selectively while leaving healthy cells unscathed, thereby circumventing some of the toxicity and side effects that are associated with non-selective forms of therapy, radiation or chemotherapy, for example. We're also interested in shutting down multiple pathways to limit the evolution of tumor resistance, to promote a more potent cancer cell death response. And we're also looking into using these synthetic RNAs as molecular probes to target new, elusive, or mutant messenger RNA sequences to give us a diagnostic handle to be able to potentially develop preventative treatment strategies. And all of this is very collaborative, interdisciplinary to help promote a translational cancer gene therapy research program from our preclinical applications into the clinical setting. Switching gears to our research efforts based on peptide chemical biology. Once again, we're motivated by working with peptides to gain a better understanding of their functional roles in interacting with other biological molecules and regulating their functionality. However, Mother Nature, once again, never designed peptides to be used as therapeutic agents. But fortunately for synthetic chemists, peptides also contain a vast array of functionality that can be fine-tuned, optimized to improve its therapeutic utility, to help promote new peptide-based drug discovery research programs. And one of the main research areas that we've dedicated our research efforts over the course of the last few years is to use synthetic peptides as both the delivery vehicles to help deliver synthetic RNAs directly into tumor cells for cancer-targeted gene therapy. We've also designed and developed synthetic peptides for cancer immunotherapy applications. And in this representation, to mimic the targeting and effector functions of antibodies, to be able to bind to a tumor cell, to be able to also bind and recruit an immune cell and stimulate an immune response, much in the same way that antibodies do, but using simple, versatile, and multifunctional peptides, thus creating somewhat of a paradigm shift, moving away from complex biologicals like antibodies and messenger RNAs, and using more simpler, short synthetic peptides and short synthetic nucleic acids for therapeutic applications. In the design of one of the lead molecular construct, this unique Y-shaped motif was capable of binding and activating natural killer cells, stimulating the secretion of inflammatory responses that were directed towards a GRP78 presenting tumor for cancer-targeted immunotherapy responses, both in vitro, in cell-based assays, and also in vivo, underscoring the potential clinical utility that these simple, versatile molecular probes can have. And in fact, that's where our research applications has been designed and developed over the course of the last few years, developing synthetic peptides as molecular probes and ligands to facilitate targeted binding, to facilitate targeted binding and activation for therapeutic applications related to cancer gene therapy and immunotherapy. And our current and future research directions here at Carleton University build upon these research themes to design and develop new and improved peptide ligands that can target multiple receptors and regulate their functionalities, to develop new and improved synthetic antibody mimics, and also setting the stage for the holy grail of cancer immunotherapy research, developing synthetic peptide vaccines. So I hope I've been able to highlight to you in a very broad general sense some of our research applications in fighting cancer in an interdisciplinary collaborative manner, bringing together a talented cast of students, both past and current members, as well as institutions, collaborators, and partners that have supported our research applications over the years, and I look forward to doing the same here at Carleton University. Thank you for your attention, and I welcome any questions.
Thank you. Any questions?
Just a technical question. So what's the size of your peptides?
They range as small as 5 mers, so pentapeptides, to as lengthy as 20 or 30 amino acid sequences. And the nice thing too is that we have an automated synthesizer that you can program the sequence, load up the amino acids, and it crunches out the sequence for you completely automatically in a couple of hours. So very easy to do.
And how do you choose which
sequence to make?
Yeah, which sequence?
It depends on our target. So once we have a target identified and sequenced, we can crunch out the sequence, like I said, our peptide sequence in a matter of a couple of hours. The same thing goes with our RNA therapeutics. We have an automated oligonucleotide synthesizer in the laboratory that can program synthetically and generate synthetic RNAs and DNAs within a matter of short hours. So once we have that target in mind and we know the sequence composition of what we'd like to make, we program the machine, we add the reagents, and it does it for us. And all of our applications here are based on cancer research, but Ken has presented an interesting talk on the Canada Pandemic Preparedness Hub. And I'd also like to highlight that because these are synthetically generated, we can quickly pivot from one target to another once we have the sequence composition being able to identify it. So these are cancer-based applications, but we can also develop synthetic RNAs and peptides for antiviral, antimicrobial, in order to fight off infectious diseases as soon as the targets are sequenced.
All right, one quick question.
Thank you. Great talk. I was actually curious on, after the synthesis is completed, how do they go through the formulation process and actually become a therapeutic or a medicine?
Okay, great question. So that's a combination of synthetic chemistry and analytical chemistry. So we use the synthesizers to manufacture the synthetic biologics, RNA, DNA, peptides, and short proteins. And the beauty of that is that it's all on solid phase. So solid phase synthesis allows you to scale up on batch manufacturing scales, making up to kilogram quantities of synthetic biologics. And the nice thing too is that you can make whatever you want. So you're not restricted by biology. You're not restricted with the naturally occurring bases, with the naturally occurring amino acids. You can add whatever modified unnatural motif you'd like to add to improve the structure-function relationships, to improve the therapeutic properties. Once those are made, it's all analytical chemistry. We use HPLC, mass spec to analyze, purify, characterize, and then once we have validity confirmed, we get into cell biology to validate their biological activity in cells, tissues, and animal models, and then we scale up. That's our pipeline.
Thank you. Thank you. So,
thank you.
Our next speaker is Corinne Millard. So Corinne converted her love of the outdoors and desire to protect and understand the environment into a great research career. She did her PhD at Carleton and is currently the director of the Geomatics and Landscape Ecology Lab. And I will let her tell you about her research.
No, I left there 4 years ago, maybe.
Oh, okay.
Yeah.
I can hear someone else. Can you guys hear me? Okay.
A company called Turnstone.
Let me see if I can make sure I know how this works. So my name is Corinne Millard. Thank you for getting my name right. That was amazing. That's very rare. And I'm in the Department of Geography and Environmental Studies at Carleton. So I'm actually part of the Faculty of Arts and Social Sciences. And I'm here today to talk about my research in remote sensing of the environment. So I started in geography, the geography department at Carleton many years ago for my PhD. I came back in 2019 as a lecturer and then in 2020 as an assistant professor. I'm one of the directors of the Geomatics and Landscape Ecology Laboratory. I'm one of the minor directors. I'm definitely not the head lead. And in the geography department, I'm actually starting my own lab, and I wanted to test out this name with you guys today. So the name that we're working on right now is the Lab for Environmental Modeling Using Remote Sensing. And what's great about that is it describes exactly what I do. So I'm going to describe in a bit what I do, but at the end of the talk, I want you to see if you think it's appropriate. The issue with this name is that the acronym spells lemurs. And we don't do anything with lemurs. So tell me if you think it's good. I'd like to take a vote or something at the end, or if anybody has any better ideas, I'm totally willing to hear them. We've been through a million different names. This group that you see on the screen is a group of masters, PhD, and postdocs who are working on a variety of different problems in remote sensing, including protected areas mapping, wildfire and soil moisture mapping, salt marsh characterization, vegetation characterization, all sorts of different things. So I'll start by just describing what is remote sensing. What is this group that is actually doing? Well, remote sensing is a science that monitors the Earth. So we have, hundreds of Earth observation satellites circling the Earth every single day, and we're acquiring this massive archive of imagery. It's continually increasing in size up to, say, petabytes now, but it has many different types of imagery, different spatial, temporal, radiometric resolutions, different types of sensors. And so all of that is to say that we are able to look at the Earth in slightly different ways. So you probably have seen images on Google Earth where it looks like what you would see with your eyes. But the common tasks that we do include creating thematic maps. So if you've ever looked at a map of, say, Ottawa or Ontario or Canada, where you have areas that are covered by agriculture, areas that are covered by forest, areas that are covered by an urban class, then that's a thematic map, and those were probably created using remote sensing. We monitor disturbances and do change detection. So you've probably read stories in the news about illegal logging in the Amazon rainforest. So a lot of that is detected using remote sensing. We also estimate and model biophysical parameters. So things like biomass, soil moisture, temperature, all of these environmental variables. We are able to estimate those. I didn't use the word measure here because we're not actually measuring these things with remote sensing. We're measuring electromagnetic radiation that's being reflected or backscattered or emitted from the surface of the Earth. I mean, we need to convert that electromagnetic radiation information into something that's meaningful to those different variables that we want to model. So the big question that I always have is, how do we extract meaningful information from remotely sensed data that is relevant to ecology, conservation, the environment, these sorts of areas? And so the image on the left is an air photo that was taken with a drone in a peatland just east of here. The image on the right is obviously a handheld camera picture. This is a pitcher plant. There's also some sphagnum mosses and Labrador tea in that picture. And the top picture there is a spotted turtle. So those two things, the spotted turtle and the pitcher plant, are actually in this air photo that you see. And so we need to be able to take this image that you're looking at and try to understand other sorts of objects. So this is where the relationship to ecology comes in. Is the question is, where are the spotted turtles? Well, we need to look at this image and find out what would be the best conditions for that spotted turtle to live in. I'm going to talk about 4 specific examples that my lab is working on. The first one is peatland ecosystem mapping. So I do a lot of work in peatlands. This is Alford Bog. So it's a peatland, which is a type of wetland that's partway between here and Montreal. And this is an image, something similar to what you would see on Google Earth. It's a medium resolution, remotely sensed image. But what we want to do is go to something like that image over there, which is a thematic map. And so these are classes, fen, treed bog, shrub bog, that you wouldn't necessarily see on a traditional thematic map. But these classes are important to ecologists and biologists. And we may actually subdivide those into whatever relevant class we have. So how do we actually go about doing that? Well, we use machine learning and other sorts of techniques. And this is where we work with people in computer science and engineering and data science to do this sort of analysis and develop techniques that are relevant for the spatial questions we're asking and the ecological questions that we're asking. So that was a relatively small example. Alfred Bog's a relatively small bog. But we have this need to know where peatlands are and the different types of peatlands and their distribution across the country. And so this map that you see here is a work in progress by one of my master's students, Nick Pontone, who's developing a boreal forest-wide peatland map. And he's looking at subclasses that are relevant to wildfire mapping, actually. He's also doing something that I think is really cool. The bottom plot that you see is vegetation heights. And so he's using spaceborne LiDAR. So if any of you have heard about LiDAR on cars, it's using lasers. Well, we have them on satellites as well. And he's able to sort of characterize the different types of vegetation that are occurring in each class. And that is important in wildfire monitoring, particularly because of the forest fire fuel situation. Another example is looking at loss of forests. So in this example, we didn't actually do any remote sensing. This is a collaboration with another scientist at GLEL, the Geomatics and Landscape Ecology Lab. And the important thing here is that previous research has shown that small forests deliver a disproportionately high ecosystem services and harbor disproportionately high biodiversity. So they're important, these small forests. What we wanted to do was look at the loss of small forests over time. So we used a remotely sensed data product. So these were already maps that were produced by another group. And we looked at between 1992 and 2020 and tried to see whether or not these forests were actually remaining or whether they were being lost faster than components of large forests. And what it showed was that in almost all of the ecosystem classes globally that we looked at, the loss was greater in small forest patches than large forest patches. And so what we recommended here is that priority should be placed on protecting these small forest patches, especially in human-dominated landscapes where people are sort of eating away at these small patches really easily. Another example, monitoring landscape change. This is in collaboration with the Nature Conservancy of Canada. And so these green dots on the map that you see are the properties that the Nature Conservancy is owning or looking after, and these are protected areas. And so what they want to do is know what's going on their property. So in some cases, there might be illegal logging going on that they don't know about or they need to know about. There might be just changes due to climate change or other anthropogenic or natural changes happening. And so what I think is really cool about this is this started as a quick project in a class. I had my 4th year remote sensing of the environment class work on producing these maps for a small set of these properties across the country. And now this has grown into a much bigger project where we're actually doing this at scale across the country for the Nature Conservancy. So in the example on the bottom, this is Musquash Estuary in New Brunswick, and it's a restored salt marsh. And so the Nature Conservancy wants to look at whether this salt marsh is actually restoring, whether it's improving. And so one of the students worked on producing this land cover map. And then the goal is to do this over time as well. So the 4th example, this is the first example that I've shown where we're doing something that's beyond a classification approach. So this is actually detecting a specific object in an image. And this is a wood lily. It's a rare lily in a very special landscape. So this is Burnt Lands Provincial Park, which is just west of Ottawa. It's an alvar. And a PhD student, Ana Hernandez, is looking at how to detect this actual plant in imagery. So she needs to use drones. She needs to use very, very high resolution imagery because this wood lily is very, very small. And it also only blooms at certain times. So she has to be out there on the few days that it's actually in bloom in order to actually capture it. Because if it's not blooming, we can't really see it. The idea here is that she wants to check and see if field-based monitoring, like traditional field-based approaches to finding these species, is better or worse than using drones. So can we reduce the amount of work that people are actually doing on the ground using drones? And she's going to be going out again this summer and hopefully collecting more imagery and trying to help answer this question of the detection of these rare species. So there's some special challenges in using remote sensing in ecological areas. And the biggest one, and this is like sort of my soapbox, is that we are imagery rich, but we're still information poor. So we have all of this remote sensing data available. All of these images are being stored, and the accessibility of them is becoming so much easier now. But we really still lack meaningfully labeled data. And what I mean by meaningful is meaningful to ecologists, conservationists, biologists, to biodiversity, to things like that. We need data that actually is important rather than just generic, forest versus agriculture. It's very easy to make a map now of forest versus agriculture versus urban. That's no big deal. But we need these specific cases where they have classes that are important to some problem. And so that's where we really need to collaborate with ecologists, biologists, et cetera. One of my biggest problems too is that a lot of the really cool places to study are remote and difficult to access, and so we don't get to go there very often. We get all kinds of imagery, but we don't have any measurements. We also work at problems across different scales. So I presented global, regional, and local studies today, and that's very common to work at all of these different scales, but it's very challenging as well because you need different techniques, different sensors in order to do that. But I see a lot of opportunities with all of these challenges that we have in connecting ecologists, biologists, conservationists with remote sensing. There's many opportunities for collaboration. There's lots of new and novel questions on the remote sensing side that still need to be answered, and there's probably new and novel applications on the ecology side that still could be answered with remote sensing as well. Spatial questions that I'm asking and that ecologists are asking are applicable across lots of different domains and at many different scales. And I think there's lots of area for new ideas to, if we come together and stick our heads together and come up with new, interesting questions. So thank you very much for listening to my talk. I hope it was interesting, even though I'm in arts. But I wanted to thank all of my students and our collaborators as well.
Thank you very much. We have time for maybe one quick question.
It's not a question. It's a suggestion. Could you put a G for geo or geographic at the front of lemurs and have it be glimmer or glimmer?
Okay, I'll look at that. That's good. Excellent. That's great.
That's a good idea. All right. So thank you very much. Sorry. Our final speaker for this session is Menno Udov. So Menno did his PhD in, well, I don't know how to pronounce it in Dutch. How would you yeah, how would you pronounce it?
So that's the VU University in Amsterdam.
VU University in Amsterdam. So his primary field of specialization is mucosal immunology and epithelial biology. I'm sure I mispronounced everything. My specialty is computer science, so I will let Menno explain what those words mean.
Thanks. All right. First off, thanks for inviting me to present our research here today. I joined Carleton less than a year ago. And so the title today is No Guts, No Glory, and that's quite literal because we study the intestine. So that's also what I'll be starting with. There we go. So you probably are all aware of your intestine, more or less. Just if you aren't, depicted here, so it starts at the stomach and ends at the colon. But I thought it'd be nice to start with some sort of random facts, more or less, that you may or may not be aware of. So essentially, it's a 6-meter long tube in adults. So yeah, that's quite long, right? And the second part is that throughout our life, we or our intestines sort of handle 35,000 kilograms of food, which is a lot. So it's actually quite important that our intestines are healthy, right? And to help us with that, we're not alone. I think there's the same amount of, or more or less the same amount of bugs or bacteria in our guts that compose the microbiota as there are cells in our body. And so this is essential for protection from foreign pathogens, but more importantly, they basically digest our food or play a large part of it, so they're quite important. So you can also see it more or less as a mutualistic entity, if you will. Oh, that's awful. You see yourself here. Anyway, but what I wanted to highlight is that this microbiota, this complex ecosystem of bacteria, it's not the same throughout. It actually depends sort of on the function of the intestine, so it's less diverse and less in amounts sort of in the small intestine, as you can see. And then once you get to the colon, it becomes a very complex ecosystem with a huge amount of different species and a large amounts of bacteria just in weight. And so one of the main functions of our intestine, other than taking up food, is also to keep our body or protect our body through something that's called tolerance. And tolerance basically just means remain tolerant so that we don't mount an immune response to something that's not ourselves, because these bacteria are non-self, right? So normally you would want to get rid of them, but we don't. So the intestine is quite important to retain this tolerance and to avoid mounting an immune response to something like food. And so these are the things we're interested in and study. And so if we go actually inside the tube, if you will, under a microscope, the small intestine looks a little bit like this. So there are these huge called villus structures, which almost look like a mountain range, if you will, and then which is not very visible, but these smaller things underneath are called crypts. And the whole point of this, of course, is to, in addition to it being very long, to increase the surface area, because if you want to be good at taking up food, the larger surface you have, the better you're at it. So that really is, serves the purpose of increasing the surface area of these large structures. But the picture I just showed you, that's actually in an adult. And what we're interested in, or one of the things we study in the lab, is how this happens during development. And we're mostly interested in what happens after birth. So if you look at your intestine, I draw this, amateuristic comic of your intestine, say a day after birth, and there's sort of three components that I want to highlight. So that starts with a very simple microbiota, because before birth it's more or less sterile, or is sterile, and right after birth the microbiota starts to come in and starts to expand and so on. So let's say this is your first week. Then you have the epithelial cells, which is this, a single layer of cells. So they are the cells that end up taking up the nutrients. And then there are these immune cells that are responsible for these aspects like tolerance, but also once we actually have a pathogen, they need to be activated and they need to mount a proper immune response. Anyway, in say the first year in life, actually these crypts only appear after birth. And then, after a year, the situation is completely different if you compare the right to the left. And so you have this increase in diversity of the microbiota. You have massive changes in the epithelium. There's more cell types showing up. It becomes more mature. That's what it's called. And you get all these other immune cells that are coming into the intestine too. And they're responsible for this tolerance phenomenon. And as you can imagine, we have to change from milk to solid foods in our nutrient uptake. So this demands sort of changes that are happening in this first year. And my lab is really interested in, what are the regulatory mechanisms that are involved in this, and especially how, say, does the microbiota influence the epithelium? How does that influence the immune cells? So how are these three sort of separate components work in concert to eventually have a healthy gut? Anyway, what can go wrong? So I'm in the Department of Health Sciences, so part of it is linked to diseases. And one of the main one is inflammatory bowel disease, which I won't go too much into detail, but the issue is there's no cure. So whenever you get it, you're basically hooked on for life, even though, you know, there's some medication that can help temporarily, but usually you're hooked. There's no cause or no known cause really. It's likely like a combination of your genetic makeup, what you eat, as well as where you live. And sadly for us, even though, you know, I came here less than a year ago, Ontario has one of the highest incidences in the world, and it's sort of assumed that it is because it's up north, so lack of sunshine, those kind of things are thought to be involved in this. So another disease that we're sort of linked to our research, and that's really based on this early life development, is necrotizing enterocolitis, and this happens a lot in premature infants. So if you're being born without your being fully developed, you can imagine things are not really done yet, if you will, and so this can cause issues with these small kids. And then the third, or actually more or less the second topic we're interested in is infection. So immune responses to whatever viruses, bacteria, fungi, helminth are very interesting, parasitic worms, and obviously this has a worldwide high incidence. So how do we study this? So going back to this amazing image of the inside of our gut, and then going in a little bit more detail, looking at these small crypt structures. And then on the right, you actually see a confocal microscopic image of the cells that are actually residing there. So you see white, green, and red. I'm sorry for the colorblind people in the room. So these are all individual cells that are depicted. And in green are actually the intestinal stem cells located. So they are located at the bottom of these crypts. And they are the ones that, you know, the whole tissue is being turned over all the time, and this all comes from these intestinal stem cells. And so what we do in the lab, we actually make mini guts in petri dishes, and this starts with, or can start with a single intestinal stem cell, and then we grow them into petri dishes into something that really resembles the intestine. So what you can see here is, I guess, the first 7 days of development that starts with a single cell, and then it slowly grows into something bigger. And then eventually, say in 2 weeks, you get these large structures, three-dimensional, that have all the components of what the intestine has in vivo. And just to show you that, if you highlight only this one aspect of it, so another crypt, we again see these green and red cells that you normally see in the tissue. So the idea is that these organoids or mini-guts really resemble the in vivo situation, and we use them to model diseases or model development. And so that's, I guess, the next part. We use them to study gut development. And so one of the examples is this early life gut maturation. So if you take epithelium from fetal tissue, you see these are round structures. Sorry, my mouth is really dry. But if you look at adult tissue, you see these complex three-dimensional structures happening. And so what we can mimic in the lab is this process of epithelial maturation. And then we can do drug screening or genetically modify it to see how this is being regulated. And the other topic that we really like to study in the lab, as I mentioned, is immune response to infection. So if you look at a normal organoid compared to an infected organoid, you see a massive change in cellular composition, and stuff like antimicrobials are being produced or mucus is being produced in the gut. And so these are the things that we want to figure out how it works, really. And the final thing is that we use microscopy also in the tissue to sort of identify where in the tissue specific immune cells reside, because that will tell us something about their function. So is this close to the microbiota? Is this close to the epithelium? Or is this more towards inside the tissue? And what cells expand during an immune response, and how does this happen during development? So all these aspects we're interested in studying. So To summarize, we use these stem cell and tissue engineering approaches and combine this really with imaging to study early life gut development and immunity to infection. That's really what it boils down to. And then acknowledgements. I had previously had a lab in Norway where a lot of this data comes from, but as I mentioned, I'm a year in. So we're actually looking for a PhD student and postdocs. If any of you know any good ones, then I'll happily take them. Yeah, and that's it. Thank you.
Thank you very much. All right, so we have time maybe for one quick question. Any?
So when you make the organoids or the mini guts, are they kind of like the whole villus with the crypt, or is it kind of just one part, or can you make like a whole tiny part of an intestine?
So you can do whatever you like, but the sort of the traditional one has gripped domains and villus domains, so it's not as pretty as in vivo, but the separate domains are present, that you have parts that are alike villus, and you have parts that are alike crypts. Sort of what I showed you with like the bottom of the crypt with having these stem cells, they're only located there and they're not anywhere else in the organoid structure. So it really nicely resembles the in vivo situation. Yeah.
Thank you.
All right, so I'd like to thank our speakers again, all 4 speakers for the session this afternoon. And I'll turn it over back to you, Jeff.
Thanks very much, Jit. Really appreciate it. I guess I'll use this. Rid of this. Okay, we're going to have one more speaking session here, and that is our panel on employer and training panel. So if our panelists can see our technical folks at the back, and if the previous panelists can return their microphones, because I think we're a little bit short, we'll get those panelists mic'd up right away. Maura, do you have? You'll just use the podium. You can also use this if you like. Sure. Okay. So maybe what I'll do first is I'm going to introduce Maura Campbell, who's going to moderate our panel today. Maura is the president and CEO of the Ontario Bioscience Innovation Organization. She joined this organization as president and CEO in February 2022. And prior to that, she was chair of the board of directors in March 2021. Dr. Campbell brings well over 30 years of experience in the biotech industry, and I've known her since her time with Turnstone, and before that, I think at VBI Vaccines as well. So please join me in welcoming Maura to the stage.
Thanks, Jeff. So please tell me if you can't hear me. I'm accused all the time of being a very quiet talker, mostly because I have 3 boys and they yell all the time, and I do not. So good morning, everyone. We're delighted you could join us today for this employer and training discussion. So as Jeff said, my name's Maura Campbell. I'm actually a PhD biochemist by training. I do have to admit I'm a U of O graduate and Queen's, not Carleton, but I did have, both my brothers went to Carleton, so I still feel like I have roots here. And I entered the world of startups shortly after I graduated, when really nobody even knew what startups did. Since then, I've worked in many different roles in various Canadian startup and venture-backed companies. So the last 2 companies I worked with, both Ottawa-based. Yes, you can have a career in industry and life sciences in Ottawa. And I joined VBI Vaccines in 2009. During the tenure that I was there, it became a public company. Currently has offices in both Boston and Ottawa. All of the research and development is still here in Ottawa. And VBI is developing virus-like particles, or EVLPs, and they were originally financed on the VeriSite platform, which was an HIV technology that was licensed from the Children's Hospital of Eastern Ontario. More recently, I was with Turnstone Biologics. I joined Turnstone in 2014, 2015, when it was literally a concept, and that was about it. They're now a New York, San Diego, and Ottawa-based company. They're still private. They're developing oncolytic virus and T-cell therapies for oncology and cancer therapies. Turnstone was originally financed based on intellectual property that was licensed from Children's Hospital Eastern Ontario, the Ottawa Hospital Research Institute, and McMaster University. And in the short years that Turnstone has existed, it's gone on to raise over $370 million USD through 4 rounds of private financing and executed 2 large pharma deals, one with AbbVie and one with Takeda. And I was able to grow and be involved in all of that activity. So currently I'm the president and CEO of the Ontario Bioscience Innovation Organization, better known as OBIO. OBIO was founded in 2009. It's a not-for-profit membership-based organization, so mostly the companies that we're involved with are either therapeutics, medical device, or digital health, and they're usually small startup companies in those really early stages of financing. And we're engaged in strategy, programming, capital P on programming, policy development and advocacy to further the commercialization of Ontario's human health science companies. And that's to position Ontario and Canada as a leader in the international life science marketplace. So we run programs under 3 pillars. Our first pillar is technology commercialization or capital access. Our second pillar is workforce development. And our third pillar is market acceleration or market adoption. So under technology commercialization, we have a capital access advisory program, which we call CAP, and that really focuses on companies that have had some level of seed funding and they're moving towards a Series A. So we take them in for a year. We do 10 to 12 companies at a time. It's mentoring, it's educational. We offer tools such as how to help set up a digital or a virtual data room for due diligence. We give them access to tools like competitive intelligence tools like PitchBook and Cortellis Deals, things that a company at that level would not be able to afford on their own. And the culmination of that program is an investment summit that we run in February of most years. We went back to in-person this year after 3 years of virtual. We had 120 investors across 3 days listening to 80 different companies pitching what they were looking for in their Series A. Under workforce development, we run a health to business bridge program, which we call H2BB. Everything in our organization is acronyms, so bear with me. And that really prepares students like yourselves and early career professionals to enter into the life science industry. So it gives them an oversight of things that are relevant that you wouldn't get in your academic PhD or postgraduate or postdoc positions. It gives an introduction to intellectual property, regulatory from both medical devices and therapeutics, project management, financing, capital structures, just a whole pile of things that you would normally not have exposure to. And then associated with our H2BB program, we run a job board and talent network. So every person that goes through the H2BB program gets a full-page talent profile that our member companies, and we had up to 200 member companies last year, they're able to search and identify prospective employees from those talent profiles. And then finally, under our market acceleration, we run our early adopter health network, which we call EAN. And this matches Canadian companies that are a little bit further along in their maturity. So they have generally a technology that's ready to be adopted and procured, which means they've figured out their manufacturing, they have regulatory approval. And we help link them to healthcare organizations to identify and procure innovation. And we support those organizations through funding and through project management to do an evaluation of the technology in a real-life setting in a hospital or healthcare organization, and then to disseminate that information across our network, which is upwards of 50 Eastern Ontario hospitals now, and with the goal of getting procurement or adoption of those technologies into the healthcare organizations. So enough about OBIO. To inspire you today, we brought together some exceptional people in the life science industry, and they're going to discuss their career paths, share their experiences in and their thoughts on workforce in the life sciences. So without further ado, I'd like to introduce our panelists.
Advisory side, I'm not on the day-to-day, but one of my students is the CEO and doing quite well. Well, I think he's doing well.
Great, thank you. And that's actually a common theme. Like Dave and I met when Dave was, I think it was I can't remember if you were a postdoc or a grad student in John's lab. And then all of that came together to form Turnstone. So a lot of times, like students, postdocs get taken along for the ride. You usually get given the reins because the professor doesn't want to actually leave his own lab. So it's an interesting theme. I'm just going to quickly go through the 4 again, and just, I know, Jen, you spoke a little bit about it, but Kathleen, if you can talk about how'd you get to the current role, and what do you like most about it? And then I'm going to combine 2 questions here. If you could go back in time and give your younger self some career advice, what would that be?
Well, how did I get here? You know, after graduate school was over and you look at the postdocs on offer at the time, I realized I had a massive student loan that was going to come due very soon. And you were able to keep it at bay as long as you register in a program, stay in school, which I did. But I dug that hole for myself. And I knew that there would be roommates in my future forever, craft dinner, no new winter boots, if I stayed and did a postdoc. Sorry to any of you. Or that's how I saw it. I met up with a high school friend who knew about patent agency because he was hired as a trainee. And I said, well, you know, maybe I could give that a try. There were no job postings for this role. Believe you me, I looked, and there wasn't the internet back then. So I kind of looked in some newspapers, didn't see any. And I made a few calls. There was an agency that was advertising in every phone book in Canada for inventors. So I wasn't an inventor, but I wanted to work with inventors. So I called that phone number, said, oh, I'm going to be in Ottawa next week, actually, so why don't I stop by? Talked my way into an interview, talked my way into a job, and never looked back. And I said to my parents, who were devastated that I was leaving science to go to the service industry, I suppose, I'll give it a couple of years, pay down my student loan, and if I want to go back into science, then I'll have like a bit of a clean slate. I won't have this stress of the debt. And I liked it, and I feel that I am still in science. So it's not a dirty word to say the service industry. You're not departing your first love of the gut and the intestine was my my love in high school, in university rather. So then, you know, how did I fit in? I guess you work with other people in the patent field. You have to train, you have to apprentice as a patent agent, and then you take some exams, qualifying exams, a little bit like the CA exam. So, but you have to have on-the-job apprentice work. And then you find a company that suits your needs. There's small companies, large companies, companies that offer good parental benefits, for example, or maternity leaves. That was kind of a big deal at the time. Now there's certainly some laws surrounding that, what has to be on offer. But so you look around and you fall in with folks that want to help you and train you. And ultimately you start looking around and you become the most senior patent agent in the firm as other people retire around you. And you realize that your role now has changed to bringing other people along and bringing them forward and learning what you know. What you said, Dave, about being expert and just running at things so that you can be the expert, like just become excellent in what you do. Can't emphasize that enough. I think maybe my advice for my younger self would be, don't think that you're not capable of being expert. I think in the pyramidal scheme of, necessarily pyramidal scheme of the institution and university and learning, there's always a sage at the top of the hill. You can be that sage, and you don't have to wait to be that sage. You've got so much information at your fingertips. You can read about it, you can write a paper on it, submit it somewhere, post it on a blog, you know, become expert, read, and so don't feel that somebody else other than you is the expert when you are fully capable of that yourself. And I might add one other thing. In one of my other hats, I work on a commercialization grant review panel with CIHR, and I've had a long term with them, almost 20 years. Now they're rolling us off. They've introduced term limits, so I'm the outgoing chair now at this time. But one thing that really helped me see was how diverse all of the technologies in Canada are, and that every single project that comes to us should be funded, is worth funding. It's modest amounts that are being asked. But we have the difficult job of, you know, sort of going through and saying, you know, what's the top of the priority list. So in some ways, I am now involved in that volunteer capacity in deciding what does get funded in some of the academic projects in Canada. So it's a real privilege to have that role as well.
Thanks, Kathleen. So Jen, I know you kind of touched on it, but just a bit of your journey to where you are right now, what you like most about it, and just if you could go back in time, what advice would you give yourself?
Yeah, so I did my PhD looking at signal transduction. So for those of you who are not familiar, and how it affects cancer, specifically breast cancer. And for those of you who are not familiar, you have a multitude of proteins within your cells. They signal to one another to tell your cell to do certain things. And it's when that signaling goes off in a direction that it's not supposed to that you have cancer, become cancer, and then oftentimes to get up from the primary location and move to other locations in the body. I was so thick in the specifics of the signaling pathways doing my PhD, and I remember having an opportunity to sit down with my PhD supervisor and said, okay, so we figure this out, then what? And then I remember him saying to me, well, then we look onto something else. I'm like, but are we going to find an inhibitor? Are we going to try to make a drug? He's like, well, yeah, in theory we could do that, but we probably won't get there in the next 10, however many years. And when I started doing a little bit more research too on small molecule inhibitors, which would be the sort of therapy at the time of my school, it became, okay, so there's all these new small molecules coming out, but okay, if you block one pathway, then this other pathway turns on, and then, okay, we'll block both pathways. Okay, well then when you do that, this other thing happens. And it just became this quagmire of, oh my goodness. And I had this moment like, this is hopeless. And that's not where you want to be when you're working in cancer therapy, right? Thinking that it's hopeless. I think the approach I was taking was not the one for me. I wasn't behind what it was that we were doing. And yet, when I went to industry, it was the same sort of company. It was a different cancer model. It was ovarian cancer. Again, small molecule approach. And I just remember being like so completely disenchanted. When I was doing my PhD, I had the fortunate opportunity to have Dr. John Bell as one of my thesis committee members. And I would go to their work in progress meetings, which, for those of you who are in graduate studies, contemplating graduate studies, super important to go to these sorts of things with your colleagues to see what they're doing, even if it's not directly related to your own work. So easy to silo yourself in those specifics and details of your own work. But I remember thinking, oh my God, another presentation by Dr. Bell's group, because of course it was massive compared to mine. But I found it really intriguing, this whole idea of using these living things, these viruses, which at the time we thought just went in and killed the cancer cells, was able to specifically target cancer cells and kill them. And then later on it was learned that, well, no, it also has this immune benefit as well. It can reteach your immune system to recognize and kill cancer. And I don't want to steal too much because this is very much the Turnstone stuff here. But I remember thinking like, wow, isn't that novel? This is exciting. And then learning a little bit more as I went, well, how do you actually go from that concept into something that's safe and effective to go into the clinic? And, I had the benefit of training with some individuals who were part of that first company that Dave was speaking about, Generex Biotherapeutics, and, they were the ones manufacturing these complex biologics. And at the time, our understanding of GMP manufacturing and all the different criteria and requirements, we were learning. We were within an academic institution. We were using a facility that, frankly, when we had to decontaminate it, paint was peeling off the walls. It was less than ideal. But, I think much like the different iterations of the company, we've learned from there. We built a new facility. And it came to a point where basically, I'd come back to the OHRI because I lovingly refer to it as this massive black hole that just sucks you back in, but in the best possible sort of way. And I started working for John Bell directly. And, he was working on a new therapy and couldn't have it manufactured somewhere that, was affordable enough for an academic. And so it was less expensive for us actually to have this facility that had just been built using government funding, commissioned and manufacture this therapy. And I remember so I wasn't part of that team specifically manufacturing or getting that together to manufacture that drug. That predated me there. But I remember when that was done, he came up to me, he's like, okay, Jen, if we're having this issue, other people in Canada, other academics, they must be too. So I want you to start a contract development and manufacturing organization. And I was like, wait, what? What is that? And it was from working with my colleagues, within the institution, working with John, working with our collaborators across the country that we slowly but surely amassed the knowledge and the skills that we needed to run one of the most successful biotherapeutics manufacturing centers in all of Canada. Frankly, we're the only ones who've manufactured therapeutic viruses that have been used in a variety of different types of clinical trials in Canada, and is actually, as Ken was speaking to earlier today, really the foundation of that CP2H hub and our ability to be prepared to respond to the next pandemic. All that to say, again, I had no idea what I wanted to do when I was in my degree. I just knew that what I was doing at the time wasn't exactly what I wanted. I wanted to do something that had, appreciable benefit to the patients, and it is really a point of pride, I think, for myself and all of my staff when we are able to say that the stuff that we're manufacturing is going into people in the very hospital in which we work and we manufacture these drugs. And that's pretty impactful to go through the cancer center and walk and rub shoulders with these patients and know that you're 2 floors above, and whether they know we're there or not, we're there and we're trying to do these things to make their life better. If I could go back in time, I wouldn't change anything. I'm glad I did what I did. I'm glad I got into the nitty-gritty of signal transduction because it led me to where I am. I'd have to say, though, and I think very much to your point, oftentimes it's very easy to let other people control your direction because you look inwards and think, I can't possibly be the expert, or when you get to a certain level, be like, I don't belong here, the whole imposter syndrome, it's very real at all levels. But I guess what I would want to say to myself is that, be bold. You're going to make mistakes, and that's okay. You'll learn from them, and then you'll move on. I would take it very hard in my studies when I didn't feel like I was, at the top. But honestly, failing was some of the best possible things that had happened to me at different points in my career and my studies, because it allowed me to be able to take that step back and critically evaluate things and realize also I failed and I'm still here and the whole world didn't, end around me. And that was a really hard lesson for me to learn, but I wish I could go back to my younger self and tell myself that, because I think I'd be a lot less stressed at the time.
Thanks, Jen. I agree too. I found like my mistakes were the things I learned the most from, not my successes. A lot of times I didn't even know why we were successful. That was the problem. So Dave, same question, just how did you get to Turnstone? What do you like most about what you're doing right now? And if you could go back in time to your younger self, what would you tell them to do?
Yeah, I mean, I don't want to repeat myself, so I think I sort of explained how Turnstone happened and how I got to my place in Turnstone. But what I haven't covered is, what is my job at Turnstone, and do I like it, and do I regret it? I mean, I was an academic scientist. I sort of still consider myself an academic scientist, but without a job, actually. If anybody's looking to hire an academic. I really loved that time, and I miss that time every day because, you get to just play all day in your mind and then put it in practice. You can have coffee in the morning, something pops in your head. That day you could be talking to your very talented, very excited graduate students, many people that are like yourselves in this room, and start down the road to making that a real thing. 99% of the time, that idea was a stupid idea, and you should have never did that in the first place. And if you thought about it a little longer, you would have come to a different decision. It doesn't matter. That's the process of learning how to decide what to spend your time on, what not. That's not what my job is at all anymore as a commercial scientist. We have a very focused, narrow idea of what needs to be done. We've done the winnowing of the 99 ideas that were stupid. We're down to the one that's worth doing. And it's all hands on deck to get that idea as far, it's still an experiment. It's just on a more grandiose scale. But to finally get the answer to that experiment, and that's what my day job is now, is to sort of pull at a number of different cross-functional strands to just do like just a bigger, more complex, more risky, scary, and expensive, most of all, experiment. And so there's a lot of parallels, but the way that it's done is very different. And I think maybe we'll have an opportunity to touch a little bit on, some of the skills, things that are gaps, and so on. There's a very different way of approaching how you deal with the problem in academia versus in the commercial space. They're both valid, they're both great, they're both effective, they're fit for purpose, but they're very different things. The crossover skills are the ones I talked about earlier. It's like the three things. Get really good at something. Be passionate about something. Hopefully those two overlap. And then whatever that third thing was, I'm sure that's the key that I forgot. But these are the things that you need to be thinking about, less more, trying to puzzle the future. I think, I've talked to my own children about this, and, as a parent who wants the best for their kids, I probably talk to them about it way too much, and they don't want to talk to me about it anymore. But they're concerned about, how do I map out this beautiful future for me or for themselves? And it just doesn't really work that way. But the things that are in your control, those you have to spend your time on. Again, getting good at something. And there's lots of parts to getting good at something. Sucking in information, yeah, that's important. If you don't have any base information, you really don't have a lot to put together in new ways. So you got to get good at that. But you got to get good at learning, and that never stops. And then, we talked about it earlier this morning, the soft skills. You have to be good at, communicating and connecting, because whatever's in your head, if that's all you've got to work with, the world's moved past that. It's just way more complicated. The problems we need to solve don't sit in any individual's head. No matter what you hear about, this scientist is amazing, that person was a captain of industry, it's not how it actually happens. And so in order to plug into that ecosystem, you've got to have those interpersonal skills. It's practice, and some of it's innate. And if it's not innate, then just, go to more parties and talk to more people. But those are important features, and that's really not much to do with, what you thought your university life was, but it's what you need to extract from it. And that is the stuff that carries you forward. But I know I'm jumping ahead because that's what we're supposed to be talking about. But it's less about my journey and more about the journeys that are out there. And there's no one journey. There's tons of them, but there's some themes that you should try to start pulling together about what's truly important to focus on.
And Dave, I totally agree. I mean, it's being open, like I found for myself, it's just being open-minded and taking on challenges that you have no background for, but you'll get there because you've learned how to learn. And so you're, as long as you're open-minded and willing to take on challenges. So Benoit, same questions, how did you get to where you are? What do you like about it? And if you could give advice to your younger self.
Sure, so I did my PhD in polymer chemistry, so synthesizing stuff. And then I did a postdoc in bendable plastic solar panels. And then I thought I would run, and so then I like the idea of being able to have a coffee and think of random things. So I became a professor. And we run a lab now where we build materials, build electronics, and we build sensors that detect cannabis. And so I think, you're learning, I enjoyed being able to come up with ideas, think of something, and then let's try to build it and see if we can get it to work, right? Sometimes they're great ideas, sometimes not so much, and your 99-to-1 is probably pretty accurate. So I also, I like, I don't like people telling me what to do, so being a professor is nice because I can sort of research whatever I want, and it's some nice freedom. We can change directions tomorrow if we want, and it's lovely because then you get to meet new people and get to collaborate on new ideas together. And I can build a sensor that detects that, maybe, and so being able to have that freedom, I think, is probably what I love the most about my job, and also getting to work with students because students are excited and have good ideas, and then I get to stand here and pretend they're all mine. So in terms of advice I'd give to myself, I would say be nice to everybody because you never know who's going to be your next client, your next boss, your next friend for life. And I think of the people I met at parties in undergrad, and some are investing in my startup, some are on the other end of a research collaboration with industry partnerships that we have, and some of them are collaborators, and this is, you never thought that was going to happen. 20 years later, you run into this person in the same boardroom. And so I would say just, go to parties and be friendly with everybody because you never know when these people are going to come back in your life.
That's great advice. I love that 99 to 1. I have a board member who's got a very successful artificial intelligence company. He says the exact same thing. He goes, I have 99 ideas, and my staff's whole job is to figure out which one is actually worth doing. So I'm going to change the perspective a bit and ask some questions from your position as an employer instead of your career path. So for Jen and Kathleen, if from patent agent perspective and from biomanufacturing perspective, can you kind of talk about like what skills gap you're seeing in early stage professionals coming into your area?
Sure, yes, and I can talk about that from two perspectives. One is the people coming in to learn and train as patent agents, and the others are the clients that I see in their, with their inventions and such. So for the most part, people that come in as patent agents have come through the academic route as a PhD. Many of our engineers might do a master's or not do a master's at all, but many of the life sciences come in with PhDs. So I'd say that the skill gap that we see the most is many of them don't know about patents and intellectual property. And you might say, well, they knew about the job. Yes, so they're a little bit further ahead than many of our inventors who might be within an institution. Their lab has created something, so now they're an inventor on something, and I hand them a draft that they have to read, and they're like, I haven't seen a patent before. So how many people in this room have seen a patent or read a patent? By show of hands, a few people have seen patents. So I assume that even fewer would be in the patent literature searching for their pet keywords from time to time. Well, today's challenge is go home, go on Google Patents. It's a separate site than Google itself, just go Google Patents. And they have this amazing search engine. It's, it pulls data from all of the public data in the world, all the patent offices that are public in the world. This was not available when I began in the industry. We were still searching in paper patents that we had to go to a location and pull trolleys full of paper patents. So this is something, you know, in the last 20 years that has been a game changer for scientists and for those 99 ideas. Maybe Google Patents will tell you before your afternoon coffee whether somebody's done it already with a series of keywords. So give that a try today, even if it's not in your scientific field of expertise. Put in something that you've been thinking about as you're, you know, retrieving golf balls from a particularly murky water trap or something like that. You know, how could I retrieve that golf ball better? There's all kinds of interesting inventions there. So that, you know, as a challenge, I think people don't know a lot about intellectual property. The body of literature is bigger than the body of academic literature, like word for word. And that's partly because patents are so verbose, but there's just millions of them to search through. They're fairly searchable, they're fairly friendly, but you can be a real asset to your lab or your organization by having that intellectual property skill. Time for a tiny anecdote about my 19-year-old daughter who studies chemical engineering. She got a job in Calgary and happened to know that they had a patent. So her first day on the job, they plunked her down in front of the patent binder and she said, I know how to read patents. And she was reading through, and then she went on Google Patents and found where you can see prior art cited against that patent and future patents against which yours was the prior art. And she showed this to her supervisor on the same day, and they're like, I didn't know we could do that. We can see who's doing what, you know, by looking on Google Patents. So, you know, a 19-year-old kid can do it. Y'all can do it. And so, you know, become familiar with intellectual property, read a few blogs about it. The patent term is 20 years, so it's not a permanent blockage for you. And I'd say what other skills? You know, versatility, I think that's a big thing. All hands on deck. I think, Benoit, did you use that term, all hands on deck? Oh, Dave, that was your term. And that did remind me that sometimes we see people coming in and they have a particular skill and that's sort of what they wish to use in their time with our company or in their time when they're working on the invention. Be curious, reach out beyond that. Don't be intimidated by it, and that is a particular skill, to be able to reach beyond what you feel you're trained for. Become competent enough, know your limits, of course, but don't stay in the box. I could go on and on, of course, but Jen, you've got some.
Thanks, Kathleen. So Jen, you can do it from like a GMP biomanufacturing perspective.
Yes, so I have the privilege or the difficulty of working in an area that was virtually non-existent, particularly in Canada, more than 15 years ago. And so I would say that, and it's changing quite rapidly. What we do, what we need, all these things are changing as the biologic therapies or the living drugs that we're making are changing as well. And it's happening at a breakneck speed. So I'm fighting against right now the fact that we don't actually have any formal training mechanisms in place in Canada to train the sorts of people that I need to fill the bums in the seats to do the job of making these biologic therapies. And so this was something that I recognized before the pandemic. I was back in 2018 and thinking that, there has to be something that we can do about this. And I have a manufacturing facility here. I have amazing staff. I have to say, in biologics manufacturing, the process is the product. I take it one step beyond that and say, well, without the people, there is no process. And I have amazing people working with me at the BMC and thought, well, what an opportunity for them to be able to pass on their expertise and train the next generation, basically. And it's a little bit self-serving, to be honest with you. We started this program with an eye to, hey, well, we'll train them up exactly the way we want. And then at the end of this training opportunity, then we have basically first right of refusal. I mean, who doesn't want a job right after finishing college or university, right? And so looking at this very much as a pipeline of highly qualified personnel, we call you folks HQP. Once we've trained you up, you are highly qualified and desirable in the sector that you've been trained. And so we started a program called CanPrime, which Ken mentioned earlier this morning. And it took buy-in from Mora at the time and Turnstone, because Turnstone was our partner in developing this program. We partnered also with MyTax, who is very big in the training space. And so because everybody bought into this concept and this idea that, well, yeah, absolutely, we see the issue coming and that we don't have the sorts of people we need to do these sorts of jobs, we were able to start this program. And I would say, when I'm looking for candidates coming to us, it is kind of difficult to differentiate one person from another because, again, right now we don't have any formal mechanisms in place to give you an opportunity to specialize in the area that I'm looking for. And so, I would say one of the things we always look for is enthusiasm. Enthusiasm to learn. When we're talking to you, you basically have 30 minutes to tell me how you're different than the other person that I'm going to be speaking to, 20 minutes later. Recognizing that we have these programs in place to train you, so we don't expect you to know everything. But to get that feel from you that, yeah, okay, I may not know this, but I think to your point, Kathleen, I can do some reading. I can, look about what it is that you do, and I can do this. I can be taught. Those are the sorts of people we're definitely looking for. I would say, we're also working with the colleges and universities, and the colleges and universities are answering the call right now. They recognize that biomanufacturing is a multi-billion-dollar industry. Canada is just starting to dip its toe. There's been so much funding thrown at folks to build these facilities, but then again, the issue is how do we actually put the people in there to do the stuff that those facilities were designed to do? I think the other big issue for us, and this is why I'm always so happy to participate in these sorts of panels, that's blocking having the right sorts of people come to my facility and facilities like it, is awareness. Because much like I was saying before, I had no idea that this was even an option. Mind you, it was much, much earlier on when I started into this area, but that's still a very real issue right now, and I think very much, again, because when you're in your studies, you can't look at different electives and be like, oh, biomanufacturing, quality assurance, GMP production, those aren't options for you. And so that's something that, at these sorts of things, I take the opportunity to say, listen, we need all types from all disciplines to make this like a legitimate sector in Canada. And that, this is a career path. We need PhDs, we need masters, we need college, we need BScs, we need everybody to be able to fill out this sector. And frankly, there's not enough people to go around for the sorts of things that are coming down the pipe right now in Canada. So I do think that awareness is probably one of the biggest blocks right now to getting the sorts of people that we need. And I also think perhaps from your perspective, looking for other opportunities, searching for, things off the beaten path, let's say, because I would say biomanufacturing is somewhat that, because again, it's not something that you're exposed to in university, is perhaps something you could look to do as well when you're trying to figure out what's my next move. Maybe it's not my final move, but what's my next move?
Thanks, Jen. Okay, different question. Dave, I'm going to ask you and Benoit, just what could the universities and colleges be doing better to prepare students to come into the industry? And Dave, you can deal with it more from like, what do you see that should be taught, or what experience or opportunity could students take that would, basically enable them to come into an early stage startup. And Benoit, if you can give it more from the academic perspective, what can be done in labs like yourself to better prepare students?
Yeah, I mean, as I was sort of saying before, your university degree, you can get a lot of different things, lots of knowledge, lots of other opportunities. Jumping into the workforce, it turns out, spoiler alert, that most of the stuff that you learned, facts that you've learned in university aren't super helpful. They're not really useful. You're going to learn that on the job, specific knowledge you need for the particular thing. And you're going to continue to do that as you progress through your career. It's always learning, learning, learning. So, the most important thing that I think you get from your university or your college that I would hope that the university continues to foster is just the ability to learn how to learn and foster the desire to constantly be curious and learn all the time. Like, you don't want to have a bunch of graduates that are burnt out, that don't want to open another book or book, I mean.
You're aging yourself.
Yeah, go to another site to learn another thing. So, like, you want people that have active, open minds. So you want, whatever happens during your education path, when you get out of university, your head has to be open, ready to suck in new things. So the universities and colleges can't mess that up. That's one thing. And then the second thing, you can get down to specific things. So, Jen has talked about specific capabilities, taking some of your biochemistry learning and understanding how that translates into a particular kind of output, manufacturing. Research space, commercial space, having opportunities in a co-op type environment, a placement, one that's functional, not just in name, but actually a commitment from both sides of that organization to focus on that person that's coming in, not just sort of checking a box saying we've got co-ops and we've got people coming through the co-ops, but carefully nurturing that experience to make sure that the person comes out of that with some new experience and it's useful. That's, I haven't seen it done often really well. And so just having co-op programs isn't enough, or just having internships isn't enough. Making sure it's a very curated experience, I think, is a responsibility from the academic institution to make sure those are useful. And some of the companies, they may not know the value of having a co-op or an intern person. Like I say, it's very, it's not a sinister thing, but it's a very focused mindset when you get into, the workplace and the industry. And, the academic institution needs to help change some minds about the value of that experience for both parties. And that then sets up a great place for students and trainees to drop into, get something really useful. And there's two things you can learn. You can learn, I really love this, or I really hate this. And both of those are incredibly valuable. And it's, to me, it's a great time to learn that because it's non-committal. It's a 4-month stint or maybe 8-month stint. And you can grind it through anything you hate for 4 months or so if you're not liking it. But if you're out in the workplace having to learn these lessons, it's there's a bit more cost to it. So if it happened as part of your training experience, I think it'd just be better all around. And then you could also start to learn, hey, I like a bit more of that. Maybe I'm going to start to make some educational choices about kind of going that way. And it's again going back to this idea about getting really good at something you really like. You kind of got to know what you like first before you can start to really focus on getting good at it. So I think maybe those are, 30,000-foot concepts about what the academic institutions can do for you.
And Benoit, same kind of question, but just like what can the universities and college, because I hear every day from students and postdocs, like they don't see any career path but academia, and if it's not what they want to do, they're really not getting that exposure in the studies that they're doing right now.
Yeah, for sure. I would say, there's lots of levels to this question, obviously, and we could talk about it forever, but I think at the undergraduate level, the co-op's a great thing. It's set up for that, right? At the graduate level, and I would argue also, I would add to that, what you said is accurate. I would also add it's also a great opportunity for the industry to see if this is a low committal, like should I hire this person, right? So, you know, the students shouldn't be looking at this as just a job, but also as an interview. Is this where I want to work, and is this what I want to do, right? And I would say, so at the graduate level, it gets a little trickier, right? Because you're in a lab and you're doing your project and you're very focused on your certain task. And it could be a lot of benefit to do an internship at the graduate level as well, because now you have more knowledge and you're more experienced and you're reading up on more stuff. You're like, you know, you should be talking to this company. I should be working at that company. And whereas in undergrad, it's overwhelming. There's the opportunity, right? Whereas when you start so I think you know, doing a co-op or doing an internship is very important at the graduate level. That being said, it's a challenge because it's a challenge for the supervisor because they don't want to give up their good talent, right? If they're a small group, they don't want to lose their people for 6 months. That person's writing good papers. I want them to stay in my lab. So there's a struggle there as a supervisor, and so, you know, being able to. So I think the institutions should find a way to incentivize professors to let their people go do internships, because it would really benefit everybody, benefit the student, benefit the reputation of the group, of the university, and it would bring back connections. And so I think it's a very important thing, but then how do you do it? So you incentivize it somehow. I would say as a student, so what you can do as a grad student is I would just talk to your supervisor, right? And I think as a supervisor, as myself, you know, if a student comes up to me and goes, you know, this company's doing something really cool, is there a way that I could do an internship there? Maybe we could do a project together with this. And, you know, maybe this is a company I didn't think about, or I didn't, you know, anyways, when I have a student that is like, I want to go there, then it incentivizes me to be like, okay, well, maybe there's a research project I can do with this company, or maybe I can call somebody or make some connections. And, you know, there's government funding, like my tax and things like that. So maybe maybe I can get that push, right? And so if the student is motivating me to be like, I really want to do something with these people, then it encourages me to make that connection out of the blue, to contact this company and be like, I have a student, you know, they'd be subsidized. Are you interested in taking a co-op for 4 months? We could work on something, and if it works out, if you like their skill set, then maybe we can do a long-term partnership. So it can be beneficial to the supervisors as well. So I would you know, suggest to the grad students is if you want to look at possibility of doing an internship, which again would be great as you know, grounding your research and seeing how it could apply to the industry or to different industries, I would approach your supervisor, right, and see if you can get something going, right, and again, you're sort of like meeting them halfway, and then that way they can help with the rest. And so I sent one of my students to Norway to build some sensors, you know, 4 months ago, and she had a great time. And so I think it's a great opportunity. And then I'm like, oh, we can do research like that too, right? And so it also helped our research program. So all this to say, I would say as a student, talk to your supervisor. There are opportunities, there are funding mechanisms. And then anybody from the institution that's listening, I would say find a way to incentivize your professors that this is a good thing, right? Because if the only thing that is giving us tenure is how many papers we're publishing, well then the system is set up poorly to encourage our students to do internships. Whereas if you incentivize the professors to have students get jobs in industry and do internships, and you incentivize professors to do that, then that's a good thing for the institution.
Thanks, Benoit. And I find too, like companies like co-ops, because there's this sad fact in HR is that despite all your efforts as a company with recruiting, interviewing with everybody, and spending all this time onboarding, 30% of the people you employ do not work out. And so co-ops really give you that kind of opportunity to decide whether this person is really going to fit the culture of the company and fit in, and gives them a chance to decide that, you know, whether they like the company and what they're doing and everything. Jeff, do we have time for, I've got one more question, or do you want to go to audience question? One more quick? Okay. Okay. So just a quick, and this is the other thing I found with co-ops too, is like new students are so much more enlightened on new areas of technology than we are. So, you know, life science, one of the areas that's really burgeoning is artificial intelligence and machine learning, which is like just in left field for a lot of old school biochemists, biologists, chemists. But it's coming in a really big way in drug discovery, and it's having some very and big pharma is embracing it as well. It's a real cross-section of categories. So the question is just technology and how it's affecting the workforce. And with Kathleen and Jen, just quickly, like what do you see as the biggest technology trend in your two areas that, you know, patents and Jen with respect to biomanufacturing?
Sure. So I'll go first again. So I guess I can see things from the inventions that come across my desk, as well as when I wear my CIHR grant review hat, what's being innovated in Canada. And I'd say the biggest sort of category is screening, so detection screening. And that's from all different perspectives, detecting who has a certain ailment that will be responsive to a treatment, detecting, screening for compounds, a big library of compounds, having a good way to detect which compound will be more likely to succeed, screening in terms of diagnosis, especially with an elderly and aging population. So screening for anything, detection of anything, that is a big deal and it is getting funded. Scale up, big area. So you think, well, we can make this on our bench. We can do this small amount. It may not be economically feasible. So a lot of inventions relate to scale up, and that can be patented. Industry is very interested in that because it relates to that unsavory world of making profit. So if you can make it in a small bench scale, it's not going to be ubiquitous until it's scaled up. So maybe that also, biomanufacturing is very much in that field.
Absolutely.
And maybe another area, again, it's not really technologically related, but one that I see a lot of is inventions that are adaptable to low-income areas. And that doesn't necessarily mean North American or the Western world low income, but if you can get a therapeutic or a vaccine or something that's helpful in other areas of the world where there's not a lot of refrigeration, where there's difficult governments, things that can be brought in, small-sized, small devices for analysis, compounds, forms that don't need refrigeration before rehydration. Those forms are very popular right now, and I see funding for that too, as well as interest. So just three main areas there.
Thanks, Kathleen. We're seeing at Obio, a lot of our medical device companies, it's like point of care, transportable units that you don't have to go to a hospital for CPR or anything like that. Jen, can you just address it just from biomanufacturing perspective?
Absolutely, and you queued me up so nicely with talking about scalability. But I would say perhaps just biomanufacturing in general. I mean, again, it's so new right now that the field is really kind of carving its own path. I think, point of care manufacturing is a very interesting aspect that is becoming a lot more prevalent. So this is, having the ability to manufacture very complex, very personalized therapies, and then delivering it to the patient, in the same location basically as you made it, in an effort to reduce the costs. But I think that's the other biggest component, and especially, working within a not-for-profit institute that I do, where we manufacture these things, I think it's another area that we're trying to innovate on is, I would say, the affordability, because what we make is so expensive. And to your point, Maura, I think it was you, Kathleen, that other nations, developing nations, can't afford biologics. And I very much believe, and in Canada, I think we're kind of brought up to believe that healthcare is a right, not a privilege. And so there's a lot of innovations from finding different cell lines, let's say, that make more of whatever it is you're making, in my case, viruses, so that the cost per dose decreases, and finding new ways to purify whatever it is that you're making such that it's safe and more effective to be used in a person. So I mean, it is really quite exciting. It's a little bit overwhelming, though, to be honest with you as well, to keep up with all the trends, all the different mechanisms of delivery of these different drugs and whatnot. But I think it's just in general a very exciting time for biomanufacturing in general.
Thanks, Jen. And then Dave and Benoit, just a quick, how should students be thinking about new technology? Should they be getting stressed that, they don't know everything? And what ways can they go about acquiring some of this information?
Sure. So I would say, when I hire a graduate student in my group, I say, I don't know what the world's going to be like when you graduate, and I don't know what job you're going to get because it probably doesn't exist yet. And I think also, if you think of let's say there's a new programming language, and we as professors, we'll put a new course together and teach this to the students, and we're going to, put a syllabus together, and you put the slides together, you put the course together, you get an approval from the Senate that you're going to teach this thing. By the time that it's actually being offered and the students take it, that language is obsolete. So this is happening all the time, and it's everywhere. And technology will always surpass you. It will always overcome. And so you have to embrace that. And just because you didn't learn it in a course, it does not mean you cannot learn it by yourself. Like we mentioned earlier, university is really just a place where you learn how to learn. And you can go and learn about AI, and you can learn about these new things, even if you didn't take a course specific to it. Because chances are the prof who's teaching it just learned it themselves too. So, they read the book before they taught the lecture. So, you can do that too. And that, we get to the end of the PhD, and the whole point is that you don't need somebody to hold your hand through a class anymore, because you now have the skills to learn something yourself. And so you can go learn from people, or learn from doing experiments yourself, ask questions and therefore find the answer, or, or just pick up the book yourself, right? So I think new technologies will continuously come, and you have to adapt.
Thanks, Benoit. And Dave, just from the company.
Yeah, just to add on top of that, technology, like you say, it's always moving, and so nobody commands, the technology. The one cool thing about it is every new technology is it's an opportunity to just, be able to see something nobody else had the opportunity to see because the technology didn't exist that last week, right? So as a trainee and onward, you can always look at every tech and say, or any innovation, and say, could I somehow use this on the problem that's super important to me right now? Can I figure out how to exploit this in a way nobody else has done that? And if you look at probably the most poignant Nature and Science and Cell papers over the last 20 years, almost all of them that people still talk about are the ones that essentially was someone taking a new technology and just applying it to a question that people have been asking over and over and over, just with ineffectual tools. It's an omics approach, it's a high throughput approach, it's an AI /omics /high throughput approach. All it is just taking the latest tools that have now become available, usually from crossing over disciplines, and then applying it to a pretty fundamental question, and that's a science paper. Pretty much simple formula. Of course, there's lots of details involved. So technology is just an opportunity. Exploit it, or dispense with it and say, that doesn't apply to me, I'm going to think about the next one. But that's what it is. And, it's nothing but excitement, in my opinion, nothing to fear.
Thanks, Dave. So, Jeff, we'll go to questions, and I'll.
Any questions for our panelists today? We got time for a couple before your lunch. I know everyone's eager to get to lunch here, but. Anyone? Yes, over here. Oh, we got a couple. Start with you, Josh.
Hi, I was just wondering how important do you think the postdoc is after doing a PhD for any of the paths that you've talked about today?
For my path, it's not.
I would say for what we look for in, let's say, faculty members, is we're looking for, if we're going to hire a colleague, if you want to be a professor, for example, the postdoc is incredibly important. It doesn't have to be a postdoc. It could be work experience. It could be something else. But to show that it wasn't just your PhD supervisor that was pulling all the strings and was really good, but that the postdoc is your opportunity to be productive at a PhD and then productive somewhere else and show that, hey, I changed fields, I did something else, and I was still able to be successful. That means I'm great. I just wasn't just a product of a great lab, right? And we see that where people come out of these monster labs in the States and they have a bunch of Nature papers, but it's like, was it you? Are you amazing? Or were you just using the fanciest tools? And so the postdoc is, as well as other industry applications, so I don't want to say just postdoc, but like it's an opportunity to prove that you can diversify your skill set, but also show the world that you can be good, you can learn anything. And I would say you can sell your journey that way, right?
I think I just view it as another opportunity to see what else you've been capable of, very much to that point. Because likely you weren't doing what we do. And so I do look for areas, okay, so your PhD was in this, but your postdoc was, okay, this is more related to something that I've done and that's more relatable to me. Is it necessary? Not necessarily. But again, it does give you that opportunity. It's almost like the very formal co-op, if you will, after you've done your PhD. It's that work experience that you can then speak to and leverage to get your next opportunity.
I'd also say that too, that, you know, it's the opportunity for you personally to do your best work. Because your PhD, you're learning how to do your craft, getting really good at some skills. But you don't really get a chance to do your best work in a PhD.
And you have to write a thesis too, right?
And you have to write that horrendous thesis. And you got a comprehensive and all these other things. You've finally got some skills and you've got runway to go do some things. It's kind of, to me, I look at it as one of the most fun times I've ever had in my life, because there's no boundaries except, you know, finding the right place to go do it. But then once you're there, that's where you get to tell your story, like you said, and you get to have some fun and you really explore. And so, you know, if you've got the opportunity to do a postdoc and you're still really hungry and interested, do not pass it up. Doesn't mean that's the only path. There's lots of paths after a master's degree, after a PhD. There's lots of places you can take those skills and plug into the ecosystem. But there's, you know, a postdoc just allows you to take a journey that you've been working very hard to get to the start of by finishing your PhD. So depends on your own personal preferences.
Okay, we'll do one more question and then we'll send it out for lunch.
My name is Joe Holmes. I'm a volunteer at the Canadian Museum of Nature. I had a question. I work with algae, type of algae called diatoms, and I'm working on a spreadsheet of, it's a catalog of all algae diatoms, and I've gone through thousands of papers. But the question is, half the papers that I go through, well actually most of them that I go through are all freely accessible. So they're there for free, and those are the ones I focus on because I can't go through thousands of papers and have to pay every time. All the other half of the papers are paywall type. So the question is, what's the advantages, disadvantages of making the paper free or using a paywall? I know somebody's trying to make money, and that's great in financing their research, but I'm just wondering what the advantages, disadvantages of doing that would be. Thank you.
May I? So believe it or not, the academics don't actually make any money from published papers. It's the publishing houses. And so then they just have different funding models, right? And so some are subscription based, so that means that like the libraries will pay for the subscription, and then it's accessible that way. The free ones are often pay to publish. So that means that the person who's publishing it is paying. And the world is moving towards that model so that everybody can have access. And so in theory, it's a good thing. The challenge becomes as a creator of the content, it gets very expensive when I have to pay $6,000 a paper and I'm publishing 25 papers a year.
Just publish less. Yeah, just don't publish anything.
Just don't publish as much.
Isn't that what they're saying?
That's what they're telling us.
Great. Well, I think we're going to end it there. Please join me in thanking our panelists and one more time for a really engaging session. Thank you all so much for your time today. We're going to move to lunch. So lunch and the poster session is going to happen for the next hour and a half, roughly. I know we're starting a little bit late. The judges will be by to your posters shortly, but please, maybe students, go get your lunch first so you can have a quick bite to eat and be ready for the judges when they come by your posters. Thank you again, everyone. poster judges, just for the poster competition, if you can wrap up in about 10 minutes and get your scores in, that would be great. Thank you.